The universe, an awe-inspiring and boundless creation, unfolds as an intricate masterpiece that spans across galaxies, stars, planets, and the vast expanse of space and time itself. Within this cosmic arena lies not only visible matter, but also the unseen forces that govern existence. Scientists, through extensive research and observation, estimate that the universe is about 13.8 billion years old. This figure comes from studying the cosmic microwave background radiation, a faint afterglow from the Big Bang that serves as one of the most vital tools for understanding the universe's earliest moments. It provides a glimpse into a time when the cosmos was in its infancy, only 380,000 years after its birth, when particles began to coalesce into atoms and light could finally travel freely. But the universe is far from a static entity. It's not just expanding, it's stretching the very fabric of reality itself. The Big Bang Theory, which proposes that the universe began as a singularity, marks the point from which everything started to unfold. The expansion of the universe continues to this day, pushing the boundaries of our understanding and challenging our perception of space and time. This ever-expanding universe presents an enigma, forcing us to confront the concept of infinity. How can something infinitely expand into space that seems, by all accounts, infinite? Compounding this mystery are the phenomena of dark matter and dark energy. While they remain largely invisible to our senses, they are thought to constitute about 95% of the universe's mass energy content. These mysterious forces shape the very structure of the universe and play a pivotal role in its future evolution. Dark matter influences the formation and movement of galaxies, while dark energy accelerates the universe's expansion. Understanding these unseen entities is a key challenge in modern cosmology, the scientific study of the universe's origins, structure, and dynamics. Through the lens of cosmology, humanity is engaged in a profound quest to unravel the mysteries that have eluded our comprehension for centuries. To understand the birth and growth of the cosmos, scientists rely on an array of advanced methods and technologies. A cornerstone of this effort is the cosmic microwave background radiation, which offers a snapshot of the universe as it was shortly after the Big Bang. This faint glow is like an ancient photograph, capturing the universe's appearance when it had cooled just enough for atoms to form, marking a pivotal moment in the cosmos' history. By examining tiny fluctuations in the temperature of the CMB, researchers can infer the distribution of matter and energy in the early universe, revealing its structure and offering clues about its evolution. Telescopes, both terrestrial and space-based, are essential for probing the depths of time and space. The Hubble Space Telescope, for instance, has captured images of distant galaxies, some of which existed just a few 100 million years after the Big Bang. These observations have allowed scientists to peer into the past, offering a deeper understanding of the formation and development of cosmic structures. Soon, the James Webb Space Telescope will provide even sharper views, potentially revealing the first stars and galaxies to emerge in the universe. These telescopic observations are complemented by computer simulations, which allow scientists to recreate the early universe, from the formation of the first atoms to the clustering of galaxies. These simulations are grounded in the laws of physics and allow researchers to simulate the vast scales of cosmic evolution, adding a layer of theoretical understanding to the wealth of observational data. Together, these tools, observational data, theoretical frameworks, and advanced simulations, allow us to slowly piece together the history of the universe. The more we learn, the closer we come to answering fundamental questions about our cosmic origins and the future of our existence in this vast, expanding cosmos. At the heart of this grand cosmic ballet are four fundamental forces that govern the interactions between particles and shape the universe as we know it. Gravity, the most familiar yet weakest of these forces, governs the attraction between objects with mass, from the fall of an apple to the orbit of planets around stars. Despite its relative weakness on small scales, gravity's reach is immense, sculpting the structure of the universe on the grandest scales. Then there is the electromagnetic force, responsible for the interactions between charged particles. This force governs everything from the formation of atoms to the light we see, and powers the electricity and magnetism that drive much of modern technology. The strong nuclear force, on the other hand, is the most powerful force. yet operates only over the short distances within an atomic nucleus. This force holds the nucleus of an atom together, overcoming the electromagnetic repulsion between positively charged protons to bind the nucleons together in a tight embrace. Finally, there is the weak nuclear force responsible for radioactive decay and the processes that power the stars. These four forces, gravity, electromagnetic, strong nuclear, and weak nuclear, act as the weavers of the universe, shaping the cosmos from the smallest particles to the largest galaxies. Their delicate balance creates the intricate and awe-inspiring structure of the universe, a structure that continues to evolve and unfold as humanity pushes the boundaries of what we know about the cosmos. Particle physics is the gateway to understanding the smallest building blocks of the universe and the forces that shape them. It dives deep into the subatomic world, exploring the fundamental particles like quarks, leptons, and bosons, and how they interact to form the very fabric of reality. These interactions not only govern the behavior of the tiniest components, but also give rise to the immense structures we observe in the cosmos. From the power that fuels the sun to the creation of the elements necessary for life, these forces shape everything around us, often in ways we are only beginning to understand. At the heart of this exploration is the Standard Model of particle physics, a comprehensive framework that explains the electromagnetic, weak, and strong nuclear forces. Developed through decades of scientific progress, the Standard Model has provided a robust theory, successfully predicting a wide range of phenomena, from the workings of atoms to the processes that drive the stars. But while it has illuminated much of the universe's inner workings, there remains a significant blind spot: gravity. Despite its elegance, the Standard Model does not account for the gravitational force, which is still governed by Einstein's theory of general relativity. This discrepancy has left a gap in our understanding, one that continues to challenge physicists today. One of the most remarkable contributions of particle physics has been the discovery of the Higgs boson, often referred to as the God particle. This elusive particle, discovered in 2012 at the Large Hadron Collider, LHC, at CERN, provides a mechanism through which other particles acquire mass. Without the Higgs boson, particles would lack mass, and the universe as we know it, without atoms, molecules, and complex matter, could never exist. This discovery was a milestone, confirming key aspects of the Standard Model and providing new insights into the very nature of mass. But particle physics doesn't just explain the present. It provides a window into the past, into the moments just after the Big Bang, when the universe was in its infancy. In the first moments after the explosion, temperatures and energies were so high that the four fundamental forces, electromagnetic, weak, strong, and gravity, were unified into a single force. As the universe cooled and expanded, symmetry breaking occurred, leading to the forces acquiring their distinct characteristics. These extreme conditions offer clues to understanding how the universe evolved from a singularity to the vast, complex cosmos we observe today. The Large Hadron Collider, the world's largest and most powerful particle accelerator, has been at the forefront of these investigations. By smashing particles together at near-light speeds, it recreates conditions similar to those immediately following the Big Bang. Detectors then capture the aftermath of these collisions, allowing scientists to study the particles that emerge and the forces that drive them. The LHC's most famous success was the detection of the Higgs boson, but its discoveries go far beyond that, probing deeper into the fundamental nature of matter and energy. However, even as particle physics uncovers the intricacies of the universe, many mysteries remain unsolved. The Standard Model cannot explain dark matter, the invisible substance that accounts for most of the universe's mass. Nor can it account for dark energy, the mysterious force driving the accelerated expansion of the cosmos. These two unknowns constitute about 95% of the universe's content, yet they remain invisible and elusive, slipping through the grasp of even the most advanced experiments. In addition, physicists are exploring theories beyond the Standard Model, such as supersymmetry and the search for a grand unification of forces. Supersymmetry posits that every particle has a superpartner, potentially providing a deeper connection between the forces and particles of nature. Similarly, the quest for a unified theory of everything, one that can reconcile the four fundamental forces, remains a holy grail in theoretical physics. Through particle physics, we continue to unlock the secrets of the universe, piece by piece, that from the smallest subatomic particles to the largest cosmic structures. The more we discover, the more we realize just how much there is to learn. Yet, each step forward brings us closer to understanding the intricate design of the cosmos and the laws that govern its existence. As we continue to push the boundaries of our knowledge, the quest for answers to these fundamental questions remains one of the most exciting and transformative endeavors of our time. The universe is vast, mysterious, and full of untold wonders, and through the lens of particle physics, we are beginning to catch a glimpse of its deepest secrets. Particle physics, in its deepest essence, is not merely a chronicle of triumphs, but a profound narrative of humanity's unyielding pursuit of understanding the mysteries of the universe. It is a story of the unknown, constantly propelling the search for a more complete theory of everything, one that could bridge the gap between the minuscule world of subatomic particles and the boundless expanse of the cosmos. The quest is not just to decipher the building blocks of matter, but to decode the very fabric of existence itself, an endeavor that aims to unlock the secrets of everything from the smallest quarks to the vast galaxies that stretch across the universe. At the heart of modern cosmology lies the Big Bang theory, the prevailing model that describes both the genesis and the ongoing evolution of our universe. This theory tells a tale that stretches back approximately 13.8 billion years, to a time when all matter, energy, space, and time were condensed into an infinitely dense point, a singularity. It was from this singularity that the universe, in a spectacular burst, began to expand and cool, initiating the very fabric of space-time itself. As the universe continued to stretch, its particles cooled, giving birth to the first building blocks of matter. In this primordial soup, subatomic particles and atoms began to form, setting the stage for the formation of stars, galaxies, and the vast structures we observe in the cosmos today. One of the most compelling pieces of evidence supporting the Big Bang theory is the discovery of the cosmic microwave background radiation, a faint afterglow of the initial explosion. This radiation, which permeates the universe, offers us a glimpse into the universe's infancy, providing a snapshot of what the cosmos looked like just 380,000 years after the Big Bang. It is the faint echo of a moment when the universe was still in its earliest, most primal state, allowing us to peer into the depths of time and space, tracing the very origins of our existence. Yet the Big Bang theory is not just about looking backward into the distant past. The evidence continues to unfold before us in the present. The observation of galaxies moving away from us, with their redshift indicating the universe's ongoing expansion, forms another cornerstone of the theory. As galaxies recede, they reveal the dynamic, ever-expanding nature of the universe, one that is not static, but constantly evolving, driven by forces beyond our comprehension. Interestingly, despite its name, the Big Bang was not an explosion in space. Instead, it was the rapid expansion of space itself, a remarkable insight that has forever altered our understanding of the universe's dynamics. The very fabric of space-time, which we once thought to be a static backdrop for cosmic events, was born in the Big Bang, expanding at a speed unimaginable. For the first fractions of a second, the universe expanded exponentially, growing from an infinitesimal point of extreme temperature and density to an unimaginably larger size. This initial inflationary period was a pivotal moment in the universe's development, laying down the vast structure of the cosmos as we know it today. Irregularities from this period were stretched out, leaving a universe that, on a large scale, is remarkably smooth and homogeneous. The cooling of the universe during this expansion allowed energy to be converted into the first subatomic particles, electrons, neutrons, and protons, in a process that would later be described by the standard model of particle physics. As these particles began to combine, they formed the first atoms, primarily hydrogen and helium, through a process known as nucleosynthesis. These elements would go on to form the stars and galaxies that light up our universe. In the aftermath of this initial inflation, the universe continued to expand, but at a slower pace, governed by the momentum of that explosive beginning. The expansion of the universe, however, is not solely driven by the inertia of the Big Bang. There is a mysterious force at work, dark energy, which is causing the expansion of the universe to accelerate. Dark energy, still a profound enigma, plays a crucial role in the ongoing evolution of the cosmos, pushing galaxies farther apart and shaping the ultimate fate of the universe. Gravity, too, has been a constant force in the post-inflationary universe. It is the force that drew matter together, forming stars, galaxies, and the vast cosmic structures that populate the universe. As galaxies continue to move apart due to the repulsive effects of dark energy, gravity works tirelessly to shape the complex architecture of the cosmos. The interplay between these two forces, expansion and gravity, continues to define the universe's evolution. Today, the expansion of the universe remains observable. As galaxies continue to recede from us, the redshift in their light serves as a clear indicator that the universe is still growing. The Big Bang Theory, supported by a wealth of observational evidence, presents a cohesive narrative of the universe's origins and its ongoing evolution. It is a theory that connects the distant past with the present, offering a framework for understanding everything from the formation of the first atoms to the ever-expanding universe we inhabit today. However, the Big Bang Theory leaves much to be desired in terms of understanding what happened before the singularity and what could have caused the initial expansion. These gaps continue to fuel speculation and drive further research in cosmology as scientists push the boundaries of knowledge in search of answers. But in its current form, the Big Bang Theory remains a cornerstone of modern cosmology, providing a unified framework for understanding the universe's evolution, from its hot, dense origins to the grand, complex cosmos we explore and observe today. It is a testament to humanity's insatiable curiosity and desire to understand the cosmos, a pursuit that continues to unfold with each new discovery. At the very heart of our understanding of the universe's origin lies the cosmic microwave background radiation, CMB. Discovered by accident in 1965 by Arno Penzias and Robert Wilson, the CMB serves as a critical piece of evidence supporting the Big Bang Theory. This faint glow of radiation fills the cosmos, acting as a cosmic relic from the universe's infancy, a snapshot of the universe when it was still in a hot, dense state. It is remarkably uniform in all directions, but upon closer inspection, tiny fluctuations emerge, revealing the early distribution of matter in the universe. These fluctuations are invaluable, providing clues about the universe's infancy, roughly 380,000 years after the Big Bang, when it cooled enough for electrons and protons to form neutral atoms, allowing light to travel freely. This moment, known as the decoupling, marks the birth of the universe as we know it, and the CMB remains the cosmic echo of that fundamental shift. But the evidence doesn't stop there. In 1929, Edwin Hubble made another groundbreaking discovery. Distant galaxies are moving away from us with their speed directly proportional to their distance. This phenomenon, known as redshift, is a direct consequence of the universe's ongoing expansion. The light from these galaxies shifts towards the red end of the spectrum as the space between us and them stretches. The significance of this observation cannot be overstated. If galaxies are moving away from each other, it follows that the universe must have been much smaller, denser, and hotter in the past. This expanding universe fits perfectly with the Big Bang Theory, which predicts an initial state of extreme density and heat, followed by an ongoing expansion. Another layer of proof comes from the abundance of light elements in the universe. According to the Big Bang Theory, in the first few minutes following the explosion, the conditions were ideal for nuclear fusion. Hydrogen, helium, and trace amounts of lithium formed in proportions governed by the density of the universe at that time. These predictions have been confirmed by observations of the oldest stars and the interstellar medium. The measured abundances of these light elements are remarkably consistent with the predictions of Big Bang nucleosynthesis, offering further validation of the theory. Together, these three crucial pieces of evidence, the CMB, the redshift of galaxies, and the distribution of light elements, form an unbreakable foundation for the Big Bang theory. In the earliest moments after the Big Bang, the universe was in an incredibly hot and dense state. It was a time when energy levels were so high that particles of matter and their corresponding antiparticles were constantly being created and annihilated in equal measure. The universe was filled with a quark-gluon plasma, a phase where quarks, the building blocks of protons and neutrons, and gluons, particles that mediate the strong force-binding quarks together, existed freely, unconfined in particles like protons and neutrons. As the universe expanded, it rapidly cooled, crossing critical temperature thresholds that allowed these particles to combine into protons and neutrons. Just a microsecond after the Big Bang, the universe cooled enough for quarks and gluons to bond, forming the building blocks of matter. As the universe continued to expand and cool, conditions became right for a critical event: Big Bang nucleosynthesis. Several minutes into the universe's expansion, protons and neutrons began to combine to form simple atomic nuclei, primarily isotopes of hydrogen, helium, and trace amounts of lithium and beryllium. This process set the stage for the chemical composition of the universe, which would influence the development of galaxies, stars, and planets. The universe's cooling process, however, was far from over. For the next several 100,000 years, the universe remained in a state where photons, particles of light, were scattered by free electrons, creating a dense fog of light. This phase, known as the photon fog, kept the universe opaque to light. But around 380,000 years after the Big Bang, the universe had cooled to approximately 3,000 Kelvin, a temperature low enough for electrons to combine with nuclei to form neutral atoms. This process, known as recombination, was pivotal. It allowed photons to travel freely, no longer scattered by free electrons. The release of these photons marks the formation of the cosmic microwave background radiation, the faint, pervasive glow that continues to illuminate the universe today. This moment, the recombination era, marked a turning point. The universe, which had previously been a seething, energetic plasma, began to transition into a more stable state. This set the stage for the formation of the first stars and galaxies. The CMB provides us with a snapshot of the universe at this crucial point in its evolution, offering us a glimpse of the cosmos at a time when it was still in its infancy, but rapidly evolving. These early moments, immediately after the Big Bang, were truly unfathomable. The universe was hotter and denser than anything we can directly observe today. The extreme conditions that prevailed allowed for the creation of the first particles of matter, which would eventually form the elements that make up everything we see in the universe. These early particles were the building blocks, the foundation of all matter, setting the stage for the universe's slow but steady evolution into the vast, structured cosmos we observe today. The formation of stars and galaxies from these primordial elements took millions of years, but it was this crucial period that laid the foundation for everything that came after. The legacy of the Big Bang is embedded in the very structure of the universe, and the evidence left behind continues to shape our understanding of the cosmos. The cosmic microwave background, the expansion of the universe, and the abundance of light elements all contribute to the comprehensive and consistent explanation of the universe's origin and evolution, confirming the Big Bang theory as the best model we have for understanding the history of our universe. In these early moments, the universe was a seething cauldron of energy and particles. Quarks, leptons, and their respective antiparticles, along with force-carrying bosons, were the primary constituents of this primordial soup. This epoch, known as the quark epoch, marked a time when the universe was so hot and dense that quarks could not bind together into protons or neutrons. Instead, quarks and gluons, the particles responsible for mediating the strong force, existed in a free state, creating what we call a quark-gluon plasma. The sheer temperature and density made it impossible for any structure to form, and the universe remained in this chaotic, energetic state for a while. As the universe expanded and cooled, something extraordinary happened. The energy dropped to a point where quarks could finally bind together, leading to the creation of protons and neutrons in a process known as hadronization. Electrons, a type of lepton, were already present in these early moments, but the conditions were still too extreme for them to combine with protons and form atoms. This step, a vital moment in the universe's history, would take place later when temperatures and energy levels decreased even further. In addition to these particles, neutrinos, another type of lepton, were also produced abundantly during these early moments. Unlike other particles, neutrinos interact very weakly with matter. This trait allowed them to decouple from the other particles shortly after their creation. They began to stream freely through space, creating a cosmic neutrino background, a faint signature akin to the cosmic microwave background radiation, but much harder to detect. These first particles, quarks, leptons, photons, gluons, were the building blocks of everything that would come to form the universe. Their interactions, governed by the fundamental forces of nature, sparked the transformation from a uniform, chaotic sea of particles into the structured cosmos we observe today: galaxies, stars, planets, and more. Just a fraction of a second after the Big Bang, the universe entered a phase so extreme and dense that it lies beyond our current understanding of physics. This period, known as the Planck era, is named after Max Planck, the founder of quantum theory. Lasting from the Big Bang's inception up to roughly 10^43 seconds, the temperature during this epoch was so high that the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were likely unified into a single force. The energy levels during this time were so immense that current theories like general relativity and quantum mechanics cannot fully describe what occurred. As time progressed, the universe entered the grand unification epoch, which spanned from about 10th in about -43 seconds to 10th in 36 seconds. During this period, the temperature of the universe dropped just enough for the gravitational force to separate from the other forces. This marked the first differentiation in the fundamental forces. It was also during this time that the universe may have experienced a phase of rapid inflation, a short but dramatic expansion of space that saw the universe's size increase by a factor of at least 10 to the 26. This inflation smoothed out any irregularities, setting the stage for a more uniform and isotropic cosmos on large scales. By 10 to the 32 seconds, the universe had cooled sufficiently for the strong nuclear force to become distinct from the electroweak force, a combination of the electromagnetic and weak nuclear forces. However, the universe was still in a plasma state with a hot and dense mixture of quarks, leptons, electrons, neutrinos, photons, gluons, and their antiparticles. This extreme environment meant that particles were constantly being created and annihilated. The forces of nature were beginning to take shape, and the fundamental properties of matter and energy were being etched into the universe's fabric. This brief moment after the Big Bang, though nearly imperceptible on the cosmic scale, set the initial conditions that would eventually give rise to everything we observe in the universe today. The formation of atoms, stars, galaxies, and the vast structure of the cosmos can all be traced back to this initial burst of expansion and cooling. The complexity and diversity of the universe we see today are direct results of that very first moment of creation. It is a testament to the immense power and significance of the conditions set in the universe's early moments, a delicate balance of forces, particles, and energy that paved the way for the cosmos to evolve into the intricate, vibrant reality we now call home. Cosmic inflation, a revolutionary theory in cosmology, offers a profound explanation for the universe's early growth, one that has changed our understanding of how the cosmos came to be. This theory suggests that within the first infinitesimal fraction of a second following the Big Bang, the universe expanded at a staggering, almost unimaginable rate. In less than 10^32 seconds, the universe's size increased by a factor of at least 10 to the 26, an expansion so rapid that it dwarfs anything we can currently observe or comprehend in the present day. The significance of this dramatic burst of expansion cannot be overstated. It solved some of the most perplexing puzzles in cosmology, such as the horizon problem, the flatness problem, and the magnetic monopole problem. Prior to the idea of inflation, these issues presented fundamental challenges to our understanding of the universe's early state. For example, the horizon problem posed a question. Why does the universe appear so homogeneous and isotropic, the same in all directions, despite different regions of space being too far apart to have ever exchanged information or energy? Inflation answered this by suggesting that the rapid expansion stretched the universe so uniformly that regions which were once in close contact could no longer be separated by vast cosmic distances. As a result, the observable universe became remarkably homogeneous, even in temperature and structure. But how did this astonishing expansion occur? It is believed that a hypothetical field known as the inflaton field was the driving force behind inflation. This field, which permeated the fabric of space itself, existed in a state of incredibly high energy. When this field decayed to a lower energy state, it triggered the exponential expansion of space. As the field's energy waned, the expansion slowed, and the energy released during this process was converted into the hot, dense plasma of particles that would later form the universe's first atoms and galaxies. This transformation was called reheating, a phase in which the universe rapidly cooled, filling space with the energetic plasma that set the stage for everything we observe today. This process explains how the universe, initially a vast and chaotic field of energy, became the structured cosmos that we know, with stars, galaxies, and planetary systems. One of the most compelling pieces of evidence supporting cosmic inflation comes from the cosmic microwave background, CMB radiation. The CMB is a faint afterglow of the Big Bang, filling the universe and carrying within it a detailed record of the universe's early state. Observations of the CMB reveal tiny temperature fluctuations and isotropies that are astonishingly uniform across the sky. These fluctuations are precisely what inflation theory predicted, the small density variations that emerged in the early universe. Inflation theory suggested that these fluctuations should be nearly identical at every scale, a prediction that has been confirmed by numerous space-based observatories and detailed maps of the CMB. What makes these observations so significant is that the fluctuations in temperature and density from the CMB match the specific predictions made by inflation. The uniformity across vast regions of space provides critical confirmation that the early universe underwent a period of rapid inflationary expansion. The confirmation of these predictions has bridged the gap between our understanding of the universe's birth and its later development, giving us a clearer view of how the universe evolved from a nearly featureless high-energy field into the structured cosmos filled with stars, galaxies, and other large-scale structures. Inflation is also essential in explaining why the universe appears so flat. In general relativity, the shape of the universe depends on the density of matter and energy. A universe with too much density would collapse in on itself, while one with too little would expand endlessly. Our universe, however, appears to be perfectly flat. Cosmic inflation explains this by suggesting that during the rapid expansion, any initial curvature of space was stretched to such an extent that the universe became flat, much like how a small patch of the Earth appears flat, even though the planet itself is spherical. The quantum fluctuations that occurred during inflation didn't just smooth out the universe, they also laid the groundwork for all the structure that followed. The tiny variations in density created during inflation were stretched to cosmic scales. Under the influence of gravity, these fluctuations eventually grew into the galaxies, stars, and other celestial bodies that populate the universe today. Cosmic inflation remains one of the most captivating aspects of cosmology. It not only provides a remarkable solution to long-standing puzzles in the Big Bang theory, but also lays the foundation for understanding how the universe evolved from a singular, infinitely dense point to the vast, intricate cosmos that we see around us. It gives us insight into the earliest moments of the universe's history, a time when the entire cosmos expanded in a burst of unimaginable speed, forever shaping the structure and uniformity of the universe as we know it. In the end, cosmic inflation is not just a theory, but a vital piece of the puzzle that helps explain the intricate, vast universe we live in. It is through the lens of this groundbreaking idea that we continue to peer deeper into the mysteries of the cosmos, unraveling the story of our universe from its birth to its current, ever-evolving state. In the vastness of the universe, the origins of its dynamic and complex structure are intricately woven into a tapestry of cosmic events. These initial perturbations, imprinted on the cosmic microwave background radiation, serve as a crucial evidence of the early universe's tumultuous beginnings. They were not only present, but meticulously mapped, offering confirmation of the theoretical predictions made by the inflationary model of the universe. This model, grounded in the idea that the early universe underwent a rapid and exponential expansion, elegantly accounts for some of the most puzzling phenomena we observe in the cosmos today. One such mystery lies in the formation of exotic particles and defects in space, such as magnetic monopoles. The theory of inflation suggested that these particles, which should have emerged in the early universe, were mysteriously absent in the present one. This posed a conundrum for scientists, who were left to wonder why these anomalies didn't persist. The answer, as the theory goes, is that inflation diluted the concentration of these exotic particles to negligible levels, effectively explaining their rarity or complete absence today. Cosmic inflation, therefore, isn't just a footnote in the story of the universe. It is a cornerstone, a foundational theory that explains not only the absence of these particles, but also sets the stage for the vast and intricate cosmos we now observe. The rapid expansion during the inflationary period locked in the initial conditions necessary for the formation of a structured, dynamic universe, one that would evolve over billions of years into the universe we now call home. As we look deeper into the timeline of the universe, beyond the inflationary era, we come to a crucial stage known as the quark epoch. This period, lasting from about 1/1,000,000,000 of a second to 1/1,000,000th of a second after the Big Bang, was marked by extremely high temperatures and densities. During this epoch, the universe was filled with a fiery quark-gluon plasma, a chaotic mixture of fundamental particles. The temperatures reached unimaginable levels, ranging from about 1 trillion Kelvin to 1 quadrillion Kelvin, so high that quarks, the very building blocks of matter, were unable to combine into protons or neutrons. Instead, quarks existed in a free state, constantly interacting with gluons, the particles responsible for carrying the strong nuclear force that binds quarks together. The quark-gluon plasma was a volatile environment, where quarks, gluons, leptons, such as electrons and neutrinos, and their respective antiparticles, were constantly created and annihilated in pairs. The universe during this epoch was still too hot and too dense for any meaningful structure to form. Atomic nuclei, let alone atoms, were a distant dream. Yet it was also the time when the four fundamental forces of nature, the strong, weak, electromagnetic, and gravitational forces, began to take on their distinct identities. Gravity, for example, had already split from the other forces during the grand unification epoch that preceded the quark epoch, marking the beginning of the universe's intricate dance between forces and particles. As the universe continued to expand and cool, the energy density eventually reached a critical point. This cooling allowed quarks to combine and form protons and neutrons, transitioning the universe from the quark epoch into the hadron epoch. This momentous change marked the beginning of the formation of hadrons. Particles would serve as the building blocks for all matter in the universe. The hadron epoch was a turning point, one that would set the stage for future epochs, ultimately leading to the synthesis of simple atomic nuclei and the formation of neutral atoms. In the early moments following the Big Bang, the temperature and density conditions of the universe underwent dramatic transformations, creating the foundational conditions for all subsequent cosmic evolution. The universe, which began as an intensely hot and dense state, slowly began to cool. Temperatures were so high that the four fundamental forces of nature were unified. However, as the universe expanded, this rapid cooling allowed the universe to settle into a less extreme state. Within minutes of the Big Bang, protons and neutrons formed, marking the dawn of an epoch known as Nucleosynthesis, during which the first simple nuclei were created. As cooling continued over the next hundreds of thousands of years, the universe's plasma state transitioned into a gas state. Electrons combined with these nuclei to form the first atoms, predominantly hydrogen and helium, setting the stage for the formation of stars and galaxies. This cooling and expansion of the universe played a crucial role in sculpting the structure of the universe we see today, setting the foundation for the stars, galaxies, and larger cosmic structures that would later emerge. The evolution of the universe, from the extreme temperatures of the early moments to the creation of the first atoms, was not a simple, linear process. It was a profound and intricate dance between temperature, density, and the forces of nature, one that would lay the groundwork for everything that followed. The transformation of the universe during these early epochs highlights a pivotal period in the cosmos's history, one that holds the key to understanding how the universe came to be and how it continues to evolve today. Quarks, the fundamental building blocks of matter, were first identified in the 1960s through experiments conducted using particle accelerators. These particles are the true elementary components of the universe, as opposed to atoms, which were once thought to be the smallest indivisible units. At a microscopic level, quarks have no internal structure, making them some of the most fundamental objects known to science. Their discovery revolutionized our understanding of matter, revealing that the universe's building blocks are far more intricate than previously imagined. Unlike atoms, which consist of protons, neutrons, and electrons, quarks are never found alone. They are the essential ingredients of hadrons, which include particles like protons and neutrons. These hadrons, in turn, combine to form the nuclei of atoms, which are the foundation of all known matter. Quarks come in 6 distinct varieties referred to as flavors: up, down, charm, strange, top, and bottom. Each flavor possesses unique properties. For example, protons consist of 2 up quarks and 1 down quark, while neutrons are made up of 1 up quark and 2 down quarks. The interaction between quarks is governed by the strongest of nature's 4 fundamental forces, the strong nuclear force. This force, mediated by particles known as gluons, binds quarks together so tightly that they can never exist independently. Instead, they are always confined within hadrons, a phenomenon referred to as quark confinement. This property makes it nearly impossible for scientists to directly observe individual quarks in isolation, so their existence and behavior are inferred through high-energy particle collisions and experiments. Studying quarks doesn't just illuminate the microscopic world, it also provides a window into the early moments of the universe. Quarks played a pivotal role in shaping the universe immediately after the Big Bang. The conditions that prevailed during this time, extreme temperature and density, allowed quarks and gluons to exist in a free state, forming what scientists call a quark-gluon plasma. This unique phase of matter only existed for a brief moment, but it was crucial in the formation of everything that followed. As the universe cooled, quarks began to combine, eventually forming protons and neutrons. This shift marked the end of the quark epoch and laid the foundation for the subsequent formation of atoms, stars, and galaxies. The quark epoch occurred just moments after the Big Bang, when the universe was a hot, dense soup of particles. Roughly 1/1,000,000,000 of a second after the Big Bang, quarks, gluons, and other fundamental particles were in an intense, unbound state. During this period, the temperature of the universe was an unimaginable 1,000,000,000,000 Kelvin. It was only as the universe expanded and cooled that quarks began to form pairs and triplets, leading to the creation of protons and neutrons. This formation of matter marks the start of the hadron epoch, a critical phase in the development of the cosmos. Protons and neutrons filled the universe, setting the stage for the formation of the first atoms, stars, and galaxies. The formation of quarks was not just an event of historical interest, but continues to be a subject of intense scientific inquiry. Researchers are still working to fully understand the intricate forces that govern this early phase of the universe and how quarks played a role in the ultimate creation of the cosmos as we know it. In parallel, another fascinating component of the quark family is the antiquark. These are the antimatter counterparts to quarks, mirroring all their properties, but with opposite quantum characteristics. For every flavor of quark, there exists an opposing antiquark with the same mass but opposite electric charge and other quantum numbers. When quarks and antiquarks meet, they annihilate each other, releasing energy in the form of high-energy photons or other particles. This interaction highlights the delicate symmetry that exists between matter and antimatter in the universe. Interestingly, although the universe seems to be dominated by matter, the existence of antimatter is not just theoretical. Antiquarks have been produced and observed in high-energy particle collisions, such as those conducted at particle accelerators like the Large Hadron Collider. These experiments recreate conditions similar to those of the early universe, allowing physicists to study both quarks and antiquarks and to delve deeper into understanding the fundamental forces at play. Understanding antiquarks is not merely an academic exercise. It has profound implications for cosmology, particularly regarding the puzzle of why the observable universe contains so much more matter than antimatter. This asymmetry between matter and antimatter remains one of the greatest mysteries of modern physics. By studying quarks and antiquarks, scientists hope to answer questions about the fundamental nature of reality and the evolution of the universe. At the heart of the interactions between quarks and antiquarks is the strong nuclear force, which is mediated by gluons. The unique property of quarks that allows them to interact in this way is known as color charge, an analogy to electric charge in electromagnetism. However, instead of being positive or negative, color charge comes in three types: red, green, and blue, and their corresponding counterparts for antiquarks. These interactions are governed by a complex and highly effective theory called quantum chromodynamics, QCD, which describes how quarks and gluons behave under the strong nuclear force. Through the lens of quantum chromodynamics, scientists are beginning to understand the deep connections between quarks, antiquarks, and the forces that bind them together. This knowledge not only enriches our understanding of the universe's most fundamental building blocks, but also offers crucial insights into the origins and evolution of the cosmos itself. The study of quarks, gluons, and their interactions continues to push the boundaries of science, providing us with answers to questions that were once considered unanswerable. At the heart of particle physics lies the strong force, an incredibly powerful interaction responsible for binding quarks together to form protons, neutrons, and other hadrons. The particles that mediate this force, gluons, do much more than simply carry the force. They also carry a combination of color and anti-color charge. This unique property allows gluons to act as the exchange particles between quarks and antiquarks. When a gluon is exchanged between a quark and an antiquark, it can alter the color charge of these particles, ensuring that the overall color charge is conserved during the interaction. But one of the most mind-boggling aspects of quark-antiquark interaction is the phenomenon known as confinement. Unlike other fundamental forces like electromagnetism, where the force between charged particles weakens as they move further apart, the strong force remains strong, or even intensifies as quarks move away from each other. This force grows so powerful that quarks cannot exist independently. Instead, they are forever confined within hadrons, composite particles like protons and neutrons. This is why we never find a lone quark. They are always bound within larger particles. As quarks and antiquarks interact, they can encounter their opposites, antiquarks of the corresponding color. When this happens, a remarkable and destructive process occurs. The particles annihilate each other. This annihilation leads to the conversion of their mass into energy, typically manifested as high-energy photons, or the creation of other particle-antiparticle pairs. This process highlights the intriguing, often destructive interaction between matter and antimatter, showcasing how these fundamental particles engage with one another in an intricate dance that underpins the structure of our universe. At a more profound level, these interactions of quarks and antiquarks play an essential role in the universe's makeup. They govern the behavior and formation of the fundamental building blocks of matter. The strong nuclear force, one of the four fundamental forces of nature, was critical in the early universe. Following the Big Bang, this force not only helped quarks combine into protons and neutrons, but also facilitated the creation of atomic nuclei. It was the key driver behind the transformation of the quark-gluon plasma, a hot, dense soup of free-floating quarks and gluons, into the matter we observe today. In the first microseconds after the Big Bang, the universe was an incredibly hot and dense place. As it began to cool, quarks began to bind together, forming protons and neutrons in a process called hadronization. This was a pivotal moment in the history of the cosmos, as these particles became the foundation for atomic nuclei. Without the strong force, these particles would have never stayed bound together, as their high kinetic energy would normally pull them apart. But the strong force kept them together, ensuring the creation of protons and neutrons, the building blocks of the atomic nuclei that would later form stars and galaxies. As the universe continued to cool and expand, protons and neutrons began to combine under the influence of the strong force, eventually forming the nuclei of the simplest elements, hydrogen, helium, and traces of lithium, through the process of nucleosynthesis. This marked the moment the universe transitioned from a chaotic particle soup into a more ordered, structured form, setting the stage for the formation of the atoms, molecules, and galaxies that would follow. One of the most fascinating properties of the strong force is its dual nature of confinement and asymptotic freedom. As quarks get closer to each other, the strong force becomes weaker. But when they move apart, it becomes even stronger. This dynamic ensures that quarks are confined within hadrons, but also allows for the formation of atomic nuclei during nucleosynthesis. Without the strong force, the universe would have remained a diffuse cloud of free quarks and leptons, incapable of forming the matter structures we see today. In the grand scheme of the universe's evolution, the strong force played an indispensable role. From the very first moments after the Big Bang, it was crucial in shaping the early universe, helping to forge the matter that would become the stars, planets, and galaxies we now observe. It is this force that has woven the fabric of the universe from the simplest particles to the complex structures we encounter in our everyday lives. As we delve deeper into the principles that govern the universe, we encounter quantum fluctuations, a phenomenon rooted in quantum mechanics. These fluctuations arise from Heisenberg's uncertainty principle, which states that we cannot simultaneously know the exact position and momentum of a particle. This uncertainty suggests that the vacuum of space is far from empty. Instead, it teems with activity as particles and antiparticles spontaneously appear and disappear over incredibly short timescales. These fleeting particles are known as virtual particles, and their existence plays a fundamental role in shaping the dynamic, bustling realm of the quantum world. This insight into quantum fluctuations helps us understand the very fabric of reality. Contrary to the classical idea of a vacuum as a void, quantum mechanics reveals a far more complex and lively scene. The vacuum is not empty space, but a dynamic stage where particles constantly emerge and vanish, contributing to the fundamental forces and interactions that govern the universe. Through the interactions of gluons, quarks, and antiquarks, and the profound influence of the strong force and quantum fluctuations, the universe unfolds as a rich tapestry of forces and particles. These interactions, though occurring at a microscopic level, have shaped everything we observe, from the formation of atoms to the creation of galaxies. It is these fundamental processes that give rise to the matter, energy, and structure of the cosmos, continuing to influence its evolution today. In the intricate, unfathomable depths of the quantum world, particles such as quarks and electrons, alongside their corresponding antiparticles, can momentarily appear from nothingness. They come into existence only to annihilate each other and vanish in an ephemeral instant. This seemingly miraculous process is governed by the energy-time uncertainty principle, a cornerstone of quantum mechanics. It allows for temporary violations of energy conservation, but only under strict conditions. If the violation lasts long enough to be detected, it is no longer allowed. This process, however, remains hidden in plain sight, as its effects are so fleeting that they evade direct observation. The implications of quantum fluctuations are far-reaching, extending across several domains of physics, from cosmology to particle physics. These fleeting variations in energy and matter are believed to have played an essential role in the formation of the universe itself. In the early moments after the Big Bang, minuscule variations in the density of matter, sparked by quantum fluctuations, were amplified by gravity over billions of years. The result, the large-scale structures we observe today, such as galaxies, galaxy clusters, and vast cosmic voids. One striking example of these fluctuations is the Casimir effect, a phenomenon where two metal plates placed extremely close together are drawn towards each other by the differential pressures of quantum vacuum fluctuations inside and outside the gap between them. This seemingly small force, a result of quantum mechanics at play, is a testament to the invisible yet pervasive power of quantum fields. Quantum fluctuations reveal a fundamental truth about the nature of reality. The universe is far more dynamic than classical physics would ever suggest. Even in its most seemingly empty spaces, where nothing is supposed to exist, the quantum realm pulses with activity, constantly generating particles, energies, and forces. This non-intuitive behavior underscores the fundamental strangeness of the quantum world, where the very fabric of reality defies our classical understanding. The role of quantum fluctuations in the early universe was not only crucial, it was transformative. During the period of cosmic inflation, an unimaginable rapid expansion that occurred just fractions of a second after the Big Bang, these subatomic fluctuations were stretched to macroscopic scales. As the universe expanded, regions that were ever so slightly denser than their surroundings due to these fluctuations began to attract more matter under the influence of gravity. Over time, this process amplified those tiny irregularities, ultimately forming the vast cosmic web of galaxies and galaxy clusters that define the observable universe. This inflationary model also predicts that quantum fluctuations are responsible for the tiny temperature variations observed in the cosmic microwave background, CMB radiation, the afterglow of the Big Bang. These variations, detected by satellites like COBE, WMAP, and Planck, support the theory of inflation and the idea that quantum fluctuations played a pivotal role in shaping the structure of the universe. The CMB provides a snapshot of the universe as it was about 380,000 years after its inception, revealing the imprints of quantum fluctuations that seeded the formation of the cosmos as we know it. Moreover, the link between quantum fluctuations and cosmic inflation also implies that the properties of the universe on the largest scales are intricately tied to the quantum world. It is a remarkable demonstration of how events at the quantum level have, in a very real sense, determined the universe's evolution. This delicate interplay between the quantum realm and the macroscopic scale of the cosmos bridges the gap between quantum mechanics and general relativity, offering a glimpse into the unity of these two powerful theories. Quantum fluctuations even influence phenomena such as the creation of particles themselves. According to quantum field theory, space is far from empty. Instead, it is filled with fluctuating fields, each one representing a different type of particle. These fluctuations can momentarily create particle-antiparticle pairs from the vacuum of space, adhering to the Heisenberg uncertainty principle. As long as these particles exist for only an incredibly brief period, they do not violate energy conservation laws, as their temporary existence falls within the permissible bounds set by quantum mechanics. One fascinating consequence of this process is the creation of virtual particles, ephemeral pairs, that spontaneously appear and then annihilate each other. While these virtual particles cannot be directly observed, their indirect effects can be measured, and they have profound physical consequences. One such example is the phenomenon of Hawking radiation, theorized by the late Stephen Hawking. At the event horizon of a black hole, quantum fluctuations can generate virtual particles where one particle is pulled into the black hole while the other escapes as radiation. This process leads to the slow loss of mass by the black hole over time, a phenomenon now widely accepted in theoretical physics. Similarly, quantum fluctuations are at play in the Casimir effect, where uncharged parallel plates placed extremely close together experience a measurable force due to the vacuum fluctuations between them. This tiny but significant force exemplifies how quantum mechanics influences the everyday world in ways we are only beginning to fully understand. These examples illustrate just a fraction of the profound impact that quantum fluctuations have on the universe. From the birth of cosmic structures to the evaporation of black holes, these fluctuations are far from inconsequential. They are the invisible threads that weave the very fabric of reality, linking the smallest scales of matter to the grandest structures of the cosmos. They remind us that even in the vastness of space, the quantum world pulses with life, influencing everything from the stars in the sky to the deepest mysteries of the universe itself. In the vast emptiness of space, the very fabric of the vacuum itself is not truly empty. Instead, it is a dynamic, fluctuating sea of energy, a realm where virtual particles are constantly appearing and vanishing. These fleeting particles, born of quantum fluctuations, shift the very nature of space. Between two plates placed in a vacuum, the energy density of these virtual particles behaves differently than outside. The fluctuation in their presence creates a subtle yet profound pressure, pushing the plates together. This pressure arises because the wavelengths of virtual particles are limited by the space between the plates, compared to the broader range of wavelengths that exist outside. This difference alters the vacuum's energy within these regions, a direct result of the quantum nature of the vacuum itself. However, these quantum fluctuations do not merely give rise to short-lived particles. They reveal the deeper, more intricate workings of the universe, where seemingly empty space is anything but empty. The quantum vacuum, far from being static, is a vibrant and restless field, underpinning the interconnectedness of all the forces that govern the cosmos. It offers us a glimpse into the profound nature of the universe, both at the microscopic scale of particles and at the vastness of cosmic dimensions. Quantum fluctuations, while responsible for the transient emergence of particles, also play a pivotal and indirect role in shaping the very building blocks of matter, particularly in the formation of protons. Protons are essential to the structure of matter, composed of 3 quarks, 2 up quarks and 1 down quark, held together by the strong nuclear force mediated by gluons. To understand how these fundamental particles came into existence, we must journey back to the early universe, mere moments after the Big Bang, during a phase known as the quark epoch. In this primordial era, the universe was a chaotic, dense soup of energy, filled with quarks, antiquarks, gluons, and their antimatter counterparts, all fluctuating in and out of existence due to the relentless energy of quantum fluctuations. As the universe expanded and cooled, it reached a threshold where these high-energy fluctuations could no longer sustain the free existence of quarks and antiquarks. The quarks, however, didn't simply disappear. They began to coalesce, forming stable combinations. The strong nuclear force, governed by quantum chromodynamics, emerged as the key force, binding quarks into protons and neutrons. This quantum-driven process was far from intuitive. Even the seemingly empty space between particles was alive with potential energy, shaping the very formation of matter itself. These protons, forged in the extreme conditions of the early universe, became the building blocks of the atomic nuclei that would later form the elements of the cosmos. The influence of quantum fluctuations, though indirect, was critical to the process, connecting the microscopic world of quantum mechanics with the macroscopic world of particle physics. As the universe continued to cool, its expansion slowed, yet it remained fundamentally tied to the cooling process that began with the Big Bang about 13.8 billion years ago. Initially, the universe existed in a state of intense heat and density, a singular point that rapidly began to expand. As this expansion occurred, the space between particles grew, causing both the temperature and energy density of the universe to decrease. This cooling process is not unlike the behavior of gases in thermodynamics. When a gas expands, it does work against its surroundings, losing energy in the process, which results in a decrease in temperature. In the case of the universe, this expansion caused the wavelengths of the radiation filling the universe to stretch. This stretching, akin to the redshift seen in the electromagnetic spectrum, marked a shift in energy, a cooling of the universe. In those early moments, the universe was so hot that matter and antimatter particles constantly collided and annihilated one another, creating and destroying in an eternal cycle. As time progressed, however, the universe cooled to the point where these particles could no longer annihilate one another so quickly. Quarks began to bind together, forming the first protons and neutrons, the fundamental building blocks of atoms. This cooling, a crucial phase in the universe's evolution, was directly influenced by the quantum fluctuations that had shaped the earliest moments of creation. From this cosmic soup of energy and quantum activity, the very structure of matter emerged, revealing how the smallest quantum fluctuations could have such a vast, far-reaching impact on the universe's development and the formation of everything we know today. However, as the universe expanded and cooled, it reached a turning point, a temperature where the intense high-energy processes that once dominated its early moments could no longer sustain themselves. This moment marked a crucial shift in the balance of the cosmos, where matter began to dominate over antimatter, setting the stage for the formation of stable particles like protons and electrons. The universe, once an incomprehensible mix of energy and particles, began to settle into the patterns we recognize today. At around 3 minutes after the Big Bang, the temperature had decreased enough to allow a pivotal event, nucleosynthesis. This brief but powerful period allowed protons and neutrons to bind together and form the first atomic nuclei. The universe was still hot, But now, for the first time, the building blocks of matter could take form, laying the foundation for everything that would come. These first nuclei were primarily made up of hydrogen and helium, along with trace amounts of lithium and beryllium, the raw ingredients for the future complexity of the universe. Yet, the cooling didn't stop there. As the universe expanded further, it cooled even more, ultimately reaching a stage where electrons, once too energetic to bind to atomic nuclei, could now join them to form neutral atoms. This process, known as the recombination epoch, would forever change the nature of the cosmos. For the first time, the universe became transparent, allowing light to travel freely through space. The photons released during this moment, known as the cosmic microwave background radiation, serve as a crucial piece of evidence for the Big Bang model and provide us with a snapshot of the universe's infancy. The cooling of the universe was not merely a matter of temperature change. It set in motion a cascade of events that would shape the cosmos. It enabled the formation of the first stable particles, which eventually condensed into galaxies and stars. These stars, in turn, synthesized heavier elements, elements that would become the building blocks for planets and, eventually, life itself. Without the cooling of the universe, the complex structures we observe today would not have been possible. The universe's cooling process was intricately linked to the expanding cosmos. As the universe cooled, it dictated the timeline of numerous cosmological milestones. Initially, the extreme temperatures of the early universe made the formation of stable matter impossible. A primordial soup of matter and antimatter constantly collided, annihilating each other in a high-energy environment. But as the universe expanded and cooled, these high-energy processes became less frequent and matter began to prevail. The cooling also ushered in a transformative period, Nucleosynthesis. For a brief window, the universe cooled enough for protons and neutrons to combine, forming the first atomic nuclei. This process produced the lightest elements, hydrogen, helium, and small amounts of lithium and beryllium, creating the raw materials for the chemical complexity that would follow. The cooling of the universe didn't just create matter, it set in motion the birth of chemical diversity in the cosmos. As cooling continued, the universe entered the recombination epoch. This was a game-changing moment. Electrons, no longer bound by too much energy, were able to combine with atomic nuclei, forming neutral atoms. This reduction in free electrons allowed photons to travel freely, marking the universe's first true transparency. The cosmic microwave background radiation, the faint afterglow of this event, still exists today as a key piece of evidence for our understanding of the early universe. The cooling of the universe also had a significant impact on larger-scale structures. It set the stage for the formation of gravitational forces, which began to condense matter into the first stars and galaxies. These massive structures would become the cosmic foundries for heavier elements, which are essential for the formation of planets and ultimately life as we know it. The cooling of the universe wasn't just a moment in time, it was the catalyst for the universe's complex evolution. It allowed the formation of the first stable particles, enabled the birth of stars and galaxies, and created the necessary conditions for life. From the simplicity of the primordial soup to the complexity of life itself, the cooling universe shows us how transformation and complexity emerged from basic physical laws and the initial conditions of the cosmos. As the universe cooled, it set the stage for one of the most fundamental transitions in the history of matter. In the moments immediately following the Big Bang, the universe was a hot, dense, and chaotic place. Particles of matter and antimatter existed in a constant state of creation and annihilation. The high temperatures were too much for stable matter to form. It wasn't until the universe cooled to below a critical temperature that the strong nuclear force was able to overcome the kinetic energy of quarks, allowing them to bind together and form nucleons, protons and neutrons. This marked the end of the quark epoch and the beginning of the hadron epoch, a critical transition in the structure of matter. As the universe continued to cool, the stage was set for nucleosynthesis. A few minutes after the Big Bang, the temperature dropped sufficiently for protons and neutrons to combine into the nuclei of light elements. The universe, once a hot soup of particles, now had its first atomic nuclei: hydrogen, helium, and small traces of lithium and beryllium. This process, though brief, set the stage for the formation of the chemical elements that make up everything we see around us. The cooling of the universe was not simply a passive event, it actively shaped the course of the cosmos. Each degree of cooling created new opportunities for matter to organize, form structures, and eventually create the elements necessary for life. From the first nuclei to the formation of stars and galaxies, cooling was the engine behind the universe's evolution, turning an initially chaotic and high-energy cosmos into a structured, stable, and complex system capable of hosting life. In the aftermath of the Big Bang, the universe began a long journey toward the complex, structured cosmos we know today. Initially, the universe was an incredibly hot, dense, and chaotic place. However, as time passed, it cooled down enough for electrons to bind with atomic nuclei, forming the first neutral atoms. This moment, known as recombination, drastically impacted the behavior of particles. It was as if the universe had gone through a profound shift. The scattering of photons, the fundamental particles of light, slowed down significantly. With this reduction in photon scattering, the universe became transparent to radiation. For the first time, light could travel freely through space, unimpeded, setting the stage for the formation of a crucial observational tool, the cosmic microwave background radiation. This radiation, a faint glow that still permeates the cosmos, offers a rare and invaluable glimpse into the universe's infancy. The cooling of the universe also had profound effects on the matter itself. Denser regions of matter, driven by gravitational forces, began to collapse under their own weight. This collapse created pockets of even higher density, which in turn attracted more particles, leading to the formation of stars and galaxies. Within these stars, nuclear fusion processes ignited, allowing lighter elements to fuse into heavier ones. This marked the beginning of the universe's chemical enrichment as new elements were created, laying the groundwork for the development of everything from planets to life itself. Each stage of cooling played a pivotal role in the universe's transformation. As the average kinetic energy of particles decreased, new types of interactions emerged, governed by the fundamental forces of nature, particularly the strong nuclear force and electromagnetic force. These forces, once barely noticeable in the early universe, now had a profound influence on shaping the cosmos. This gradual cooling and transition from a hot, uniform plasma to a vast and intricate universe teeming with stars, galaxies, and the potential for life marks one of the most critical evolutionary periods in the history of the universe. It was during this cooling period that quarks, the most fundamental building blocks of matter, began to come together to form composite particles known as hadrons. This phase is known as the hadron epoch, which took place between roughly 1 microsecond and 1 second after the Big Bang. During this epoch, the universe had cooled enough from its earlier blistering temperatures, allowing quarks, which were previously separated due to the overwhelming kinetic energy of the early universe, to bind together. Before this cooling, the universe was so hot and dense that quarks couldn't combine into stable particles. Instead, they existed in a state called the quark-gluon plasma. In this soup-like state, quarks, antiquarks, and gluons, the particles that mediate the strong nuclear force, roamed freely. As the universe expanded, it began to cool down, and the kinetic energy of these particles decreased. Once the temperature of the universe dropped to around 10^12 Kelvin, the strong nuclear force began to take over. The force, mediated by gluons, was strong enough to overcome the remaining kinetic energy, allowing quarks to stick together and form hadrons. This process initiated the formation of two primary types of hadrons, baryons and mesons. Baryons, such as protons and neutrons, are made of 3 quarks. A proton consists of 2 up quarks and 1 down quark, while a neutron consists of 1 up quark and 2 down quarks. Mesons, on the other hand, are made of 1 quark and 1 antiquark. These mesons played a crucial role in mediating the strong force between protons and neutrons within atomic nuclei. This transition from quarks and gluons to the more stable forms of matter was one of the most significant moments in the universe's evolution, as it set the stage for nucleosynthesis, the process that created the first atomic nuclei. Hadrons are not just essential in the formation of atomic nuclei, they are the very foundation of matter as we understand it. The strong force, one of the four fundamental forces of nature, is responsible for holding quarks together within hadrons. Its strength is so immense that quarks are never found isolated in nature, a phenomenon known as quark confinement. The strong force acts not only to hold the quarks together within a single hadron, but also ensures that these composite particles, like protons and neutrons, are stable enough to form the building blocks of matter in the universe. As we move forward from this point in the timeline of the universe, the influence of these fundamental forces would continue to shape the cosmos. Stars and galaxies would continue to form, heavier elements would be forged in the hearts of stars, and the universe would eventually evolve into the richly complex system of celestial bodies and life that we observe today. But it all began with these first subtle steps in the cooling and consolidation of matter, a journey that continues to unfold across the vast expanses of space and time, but also works between hadrons, keeping the atomic nucleus intact, defying the otherwise dominant, repulsive electromagnetic force between the positively charged protons. The study of hadrons is pivotal in particle physics, as it unravels the fundamental strong nuclear force and its role in shaping the universe. This force is what governs the behavior of matter under extreme conditions, such as those found in neutron stars or during the earliest moments of the universe, right after the Big Bang. At the heart of particle physics, experiments conducted in colossal particle accelerators, such as the Large Hadron Collider, LHC, probe the essence of matter. Here, hadrons are collided at mind-bending speeds, providing scientists with invaluable insights into the forces that bind the very building blocks of our universe. These experiments reveal not only the intricacies of how matter behaves, but also how it interacts on the subatomic level, shedding light on the most profound mysteries of the cosmos. Diving deeper into the heart of matter, we uncover a captivating world of elementary particles, quarks. These tiny particles form the foundation of everything in existence, acting as the very building blocks of matter itself. Quarks come together to form hadrons, the particles that are the cornerstone of the universe's structure. There are 6 known types of quarks: up, down, charm, strange, top, and bottom. The way these quarks interact with one another is governed by the strong nuclear force, one of the 4 fundamental forces of nature. This force, mediated by particles called gluons, keeps quarks bound together in a way that allows them to form larger particles like protons and neutrons. Hadrons are primarily classified into 2 families, baryons and mesons. Baryons, like protons and neutrons, are made up of 3 quarks, while mesons consist of a quark-antiquark pair. These combinations are not random, but are based on strict rules dictated by quantum chromodynamics, QCD, the theory that explains the interactions between quarks and gluons. The interplay of these particles, orchestrated by the laws of physics, forms the invisible framework of our universe. From the atomic nucleus to the extreme environments found within neutron stars, this framework governs the structure and behavior of all matter. The distinction between baryons and mesons highlights the variety of particles that constitute our universe. Both are types of hadrons, but they differ in composition and properties. Baryons, like protons and neutrons, are composed of 3 quarks, which give them a half-integer spin and categorize them as fermions according to quantum mechanics. This classification means baryons follow the Pauli exclusion principle, which states that no 2 identical fermions can occupy the same quantum state simultaneously. In contrast, mesons are formed from a quark and an antiquark pair. This composition results in mesons having an integer spin, classifying them as bosons. Unlike fermions, bosons are not bound by the Pauli exclusion principle and can occupy the same quantum state in large numbers. This fundamental difference in their quantum nature explains the distinct roles that baryons and mesons play in the universe. Baryons form the bulk of visible matter, constituting the atoms that make up stars, planets, and living organisms. Mesons, on the other hand, act as force carriers. They mediate the strong nuclear force that binds protons and neutrons together within the nucleus of an atom. Despite their short-lived existence, mesons play an essential role in particle interactions, particularly in high-energy environments like those found in particle accelerators or during cosmic ray collisions in Earth's atmosphere. The formation of protons, one of the universe's most stable and significant particles, is an extraordinary process that occurs at the quantum level. Protons are baryons composed of 3 quarks, 2 up quarks and 1 down quark. This specific arrangement imparts the proton with its distinct positive electric charge. The creation of protons begins in the tiny quantum-scale fluctuations within the early universe's quantum foam. At this scale, the strong nuclear force, the most powerful of nature's 4 fundamental forces, takes charge. Gluons, the particles that mediate the strong force, act as the glue that holds quarks together. They exchange between quarks in a continuous cycle, binding them into a stable state within the proton. Despite the repulsive electromagnetic force that tries to push the positively charged quarks apart, the strong nuclear force prevails at short distances. This dominance ensures the stability of protons even in the face of conflicting forces, allowing them to maintain their bound state. The behavior of quarks and gluons within protons reveals the stunning complexity and resilience of matter at the subatomic level, providing a glimpse into the fundamental forces that shape the universe itself. The fundamental forces of nature come together in a remarkable dance to shape the universe as we know it. At the heart of this cosmic symphony, protons and neutrons, the building blocks of atomic nuclei, play a pivotal role in determining the structure and evolution of matter throughout the cosmos. This intricate process begins at the subatomic level, where quarks, the elementary particles that form protons and neutrons, interact through the powerful forces of quantum mechanics. It is this delicate interplay of quarks and gluons governed by the laws of quantum physics that gives rise to protons, particles with remarkable stability, so stable in fact that their lifetime extends far beyond the age of the universe itself, making them one of the foundational components of matter. This stability forms the cornerstone of atomic structure, from the simplest hydrogen atom, a single proton and electron, to the complex nuclei that make up the heavier elements. The presence and stability of protons are what allow the universe to take shape. Neutrons, closely related to protons, share the same quark-based structure but differ in their arrangement. Where protons are made up of 2 up quarks and 1 down quark, neutrons consist of 1 up quark and 2 down quarks. This subtle difference in their quark configuration gives neutrons a key property: neutrality. Unlike protons, which carry a positive charge, neutrons are electrically neutral, which profoundly influences their behavior within atomic nuclei. The formation of neutrons is an intricate process that highlights the interplay of the fundamental forces. The strong nuclear force, mediated by gluons, binds the quarks within a neutron, overcoming any repulsive forces that might otherwise tear them apart. This interaction ensures that neutrons are more massive than protons, though they are also less stable. Outside the nucleus, neutrons are unstable and decay into protons under certain conditions. However, within the atomic nucleus, neutrons are critical for balancing the forces that stabilize atoms. Neutrons are produced in various astrophysical processes, but perhaps the most spectacular is during a supernova explosion. Under these extreme conditions, protons and electrons merge to form neutrons, accompanied by a burst of neutrinos. This process is one of the key events in stellar evolution, producing the raw materials that form the elements that make up everything in the universe. Within the atomic nucleus, protons and neutrons engage in a delicate balance, constantly interacting to form the variety of elements that populate the periodic table. This interaction is governed by the strong nuclear force, which is responsible for binding these particles together and determining the type of element and its isotopic variations. The number of protons in an atom's nucleus defines its element, while the number of neutrons determines its isotope. In the fiery depths of stars, protons fuse together to create heavier elements, a process that releases enormous amounts of energy and light, illuminating the heavens. As stars evolve, they engage in increasingly complex nuclear fusion processes, forming not just lighter elements like helium, but also the heavier elements that are crucial for life. The fusion of hydrogen into helium is the primary energy source of stars, including our sun. However, as stars age, they undergo more complex fusion reactions that produce even heavier elements, including those that make up the very atoms in our bodies and the Earth itself. From calcium in our bones to iron in our blood, The elements necessary for life are forged in the crucible of stars. Neutron decay also plays a critical role in shaping the universe's elements. Through beta decay, neutrons can transform into protons or vice versa, a process governed by the weak nuclear force. This decay contributes to the abundance and stability of elements in the universe, influencing everything from the energy distribution within celestial bodies to the thermal evolution of stars. This ongoing interaction between protons and neutrons is a testament to the intricate and delicate balance of forces at play. It not only shapes the atom, but also fuels the processes that power stars and create the elements that form planets, life, and all of matter. It is this balance, this fundamental interplay, that continues to shape our understanding of the cosmos. Nuclear fusion, the process by which atomic nuclei merge to form heavier elements, is the universe's most powerful energy-producing mechanism. At the core of stars, including our Sun, nuclear fusion transforms hydrogen nuclei into helium, releasing an immense amount of energy in the process. Unlike nuclear fission, which splits heavy atomic nuclei into lighter ones, fusion fuses lighter nuclei to create heavier ones. This process is far more energy efficient and produces vastly more energy. To achieve fusion, atoms must be brought to incredibly high temperatures and pressures, conditions found only at the core of stars. Under these extreme circumstances, the electrons that normally orbit atomic nuclei are stripped away, creating a plasma. In this state, the nuclei are so densely packed that the repulsive electromagnetic force between their positively charged protons is overcome by the powerful, strong nuclear force, allowing them to collide and fuse. This process not only powers stars, but also drives the creation of all the elements beyond hydrogen and helium. The fusion of nuclei in stars creates heavier elements, and as stars evolve, this stellar alchemy produces the elements that make up the material world. The energy released by fusion reactions is what powers stars and provides the light and heat that sustain life on Earth. It is through this process that stars transform hydrogen into helium and eventually create the diverse array of elements that form everything from planets to living organisms. Nuclear fusion, in essence, is the cosmic engine that drives the universe's energy production, shaping the very fabric of existence itself. But also it plays a crucial role in the creation of nearly all elements heavier than hydrogen in the universe through a series of intricate fusion reactions. For example, in the Sun, hydrogen nuclei fuse together to form helium in a multi-step process known as the proton-proton chain reaction. This process, however, is not exclusive to our Sun. In more massive stars, more complex fusion cycles unfold, such as the carbon-nitrogen-oxygen CNO cycle, which significantly contributes to the cosmic abundance of elements. Humanity's quest to harness nuclear fusion on Earth seeks to replicate this stellar process, potentially offering a near-limitless source of clean energy. Despite the immense technical challenges involved in achieving the extreme conditions needed for controlled fusion, its successful application could revolutionize energy production, providing a sustainable, environmentally friendly solution to the world's energy needs. The story of nuclear fusion in the early universe is rooted in a pivotal phase known as Big Bang nucleosynthesis. This epoch, which unfolded roughly 3 to 20 minutes after the Big Bang, around 13.8 billion years ago, was vital in shaping the universe's elemental composition. During this time, the universe was cooling from an unfathomably high temperature and density, setting the stage for the formation of the first atomic nuclei. In the first moments following the Big Bang, the universe was a dense plasma of quarks and gluons, but as it expanded, it cooled sufficiently for quarks to combine into protons and neutrons. However, it was still far too hot for electrons to combine with these nuclei, resulting in a plasma of charged particles. As the universe continued to expand and cool, it eventually reached a critical temperature and density where nuclear fusion could begin. The very first fusion process involved protons, hydrogen nuclei, and neutrons coming together to form deuterium, a heavy isotope of hydrogen, releasing a small but crucial amount of energy. This deuterium then acted as a building block, fusing with more protons and neutrons to form helium-3 and tritium, hydrogen-3, which could then merge to produce helium-4, the most stable and abundant isotope of helium. Big Bang nucleosynthesis was a brief but monumental event. The rapid expansion and cooling of the universe meant that the conditions for fusion existed for only a short time. Nevertheless, this brief window produced nearly all the helium in the universe, alongside trace amounts of other light elements like deuterium, lithium, and beryllium. The ratios of these primordial elements, as predicted by theories of Big Bang nucleosynthesis, match remarkably well with astronomical observations, providing solid evidence supporting the Big Bang theory. The process of nuclear fusion in the early universe was fundamentally different from that in stars. While stars continue to fuse elements over billions of years, Big Bang nucleosynthesis was a one-time event, occurring within a rapidly changing environment that set the stage for the chemical evolution of the cosmos. In the first moments after the Big Bang, protons, hydrogen nuclei, played a critical role in the orchestration of early nuclear fusion, laying the foundation for the elements that would come to define the universe as we know it. In the aftermath of the Big Bang, protons were abundant and ready to engage in the great cosmic symphony of creation. The universe was hot and dense enough for nuclear fusion to occur, but only for a fleeting moment. In this high-energy backdrop, protons initiated the chain of reactions that led to the formation of helium, the second most abundant element in the universe. The process began with protons colliding and fusing with neutrons to form deuterium, a heavy isotope of hydrogen, releasing a photon in the process. Despite its simplicity, the formation of deuterium was a bottleneck in the early universe. The high temperatures of the universe meant that deuterium nuclei were frequently broken apart by energetic photons before they could undergo further fusion. Once the universe expanded and cooled sufficiently for photon energies to drop below the threshold capable of breaking apart deuterium, the path was cleared for subsequent fusion steps. With deuterium now established as a crucial stepping stone, protons could continue to combine with it, progressively building up the universe's initial stock of helium. This series of fusion reactions laid the foundation for the elemental makeup of the cosmos, setting the stage for the creation of the stars, planets, and everything we see around us today. Through this tumultuous yet awe-inspiring process, the universe's chemical evolution began, marking the first moments of its vast and ongoing journey. What we see in the cosmos today, our stars, planets, and the very elements we are made of, are all the product of these early moments of nuclear fusion. And while humanity still seeks to master this powerful force on Earth, the universe has already shown us the immense potential fusion holds in shaping the very fabric of existence. In this fascinating chapter of cosmic history, a pivotal transformation unfolded. A transformation that began with the simplest of elements, hydrogen. This moment marked the dawn of nuclear fusion, the process that would forever alter the fate of the universe. In the earliest moments after the Big Bang, protons, small yet mighty, played an essential role in what can only be described as cosmic alchemy. Their interactions and fusions formed the building blocks of the universe, setting the stage for the creation of the very elements that would eventually give birth to stars, galaxies, and life as we know it. The emergence of these first elements, forged in the heart of the earliest stars and through the fiery crucible of the universe's initial seconds, can be traced back to the Big Bang itself. This cataclysmic event, which set the universe in motion, not only marked the birth of all space and time, but also set in motion a cascade of nuclear reactions. These reactions, which began in the unimaginably hot and dense state of the early universe, produced hydrogen, the simplest element that would dominate the cosmos for eons to come. As the universe rapidly expanded and cooled, conditions shifted, allowing for the creation of nuclei. Hydrogen, with its single proton, dominated this early soup of particles, but it was the protons that would soon become the architects of the universe's chemical future. Under the intense pressure and heat, protons began fusing with neutrons, giving rise to deuterium, also known as heavy hydrogen. This marked a crucial turning point in cosmic history. Deuterium's creation was a necessary precursor for the next steps in nuclear fusion. From deuterium, the path to the creation of helium-4, a stable and abundant nucleus, began. In a series of complex but orchestrated reactions, deuterium nuclei fused with protons, creating helium-3. These helium-3 nuclei would then collide, merging to produce helium-4 and releasing additional protons back into the environment, fueling the ongoing cosmic furnace. This was no ordinary process. It was the spark that would ignite the evolution of the universe's elemental composition. Although helium and hydrogen were by far the dominant elements, trace amounts of lithium and beryllium also emerged through these fusion processes, albeit in far smaller quantities. The conditions of the early universe simply couldn't sustain the extreme pressures and temperatures required to create heavier elements, thus limiting the formation of anything beyond these lighter elements. Yet, even with these constraints, the elemental mixture created in the universe's first few minutes, a cosmos primarily composed of hydrogen, helium, and traces of lithium and beryllium, would shape the universe for eons. This composition laid the foundation for everything that would follow, from the birth of stars to the formation of galaxies, and ultimately, the complex elements necessary for life. Even today, the exact ratios of these primordial elements, governed by the laws of physics and the universe's initial conditions, remain observable in the oldest structures of the cosmos. They provide a unique window into the infancy of the universe itself, offering an unspoken connection to the distant past. The preeminence of hydrogen as the most abundant element in the universe is no mere accident. Its simplicity and the conditions that prevailed in the aftermath of the Big Bang made hydrogen the first element to emerge. Composed of only one proton and one electron, hydrogen's atomic simplicity made it the most straightforward element to form in the early universe. As the universe cooled and expanded, protons and neutrons began to combine, forming the first atomic nuclei. Hydrogen, being composed of a single proton, was readily formed and, due to the abundance of protons, came to dominate the nascent universe's elemental makeup. Hydrogen's reign was further cemented through the conditions that prevailed during the Big Bang nucleosynthesis. These extreme conditions were too brief and transient to support the formation of heavier elements. Helium, the next simplest nucleus, formed in small amounts, but the universe at this stage simply didn't have the necessary pressures to create more complex elements like carbon, oxygen, or iron. Instead, it was hydrogen and helium that became the foundational elements in the cosmos, with only trace amounts of lithium formed in the initial moments. As the universe continued to evolve, stars became the next great engines of creation. Within the core of stars, nuclear fusion carried on the work that began in the earliest moments of the universe. Stars fused hydrogen into helium and, over the course of millions to billions of years, created heavier elements. Through their life cycles, stars transformed hydrogen into the elements needed to form planets, life, and everything in between. Yet, even as stars created heavier elements through fusion, hydrogen remained the most abundant element in the universe, its simplicity and ubiquity ensuring its enduring presence. Thus, hydrogen not only emerged as the first element in the universe, but it also continues to dominate the cosmic landscape. The simplicity of hydrogen, combined with the extreme conditions present at the birth of the universe and its ongoing role in stars, ensures that it remains the most abundant and influential element in existence. From the earliest moments of creation to the present day, hydrogen remains at the heart of the universe's ongoing evolution, shaping the cosmos and fueling the very stars that light our sky. The story of hydrogen is, in many ways, the story of the universe itself, a tale of simplicity, transformation, and the beginning of everything. But hydrogen, despite its simplicity, remains the most abundant element in the universe, and its formation played a crucial foundational role in the development of the cosmos. In the aftermath of the Big Bang, the universe was a vast, almost unimaginable expanse of hydrogen gas, dotted with helium and trace amounts of lithium. This initial composition was far from random. It laid the groundwork for everything that followed. It was a cosmic canvas, waiting for the brushstrokes of gravity, fusion, and time to shape the universe into what we know today. From the very beginning, hydrogen's influence was profound. It wasn't just the building block of everything we see now. It was the raw material for the first stars, the very first beacons of light in an otherwise dark cosmos. Gravitational forces began to draw these hydrogen clouds together, compressing them until the temperature and pressure were so intense that nuclear fusion ignited. This moment, when the first stars were born, known as population 3 stars, marked the dawn of a new cosmic era. In their nuclear furnaces, these stars transformed hydrogen into helium, and as they aged, they began forging heavier elements, elements that would eventually become the building blocks of planets, galaxies, and life itself. But hydrogen's role didn't stop there. The way this gas was distributed throughout the universe helped define the grand structure of everything. Early in the universe's history, slight variations in the density of hydrogen gas led to the formation of gravitational pockets. These pockets pulled in more gas, growing denser and denser, eventually creating galaxies. These vast hydrogen clouds, now clustered in galaxies, became nurseries for new generations of stars. Each new star carried with it the memory of its hydrogen origins, fueling its energy with the same process that ignited the first stars. In a more abstract sense, hydrogen's simplicity and abundance serve as an invaluable tool for astronomers. Its absorption and emission spectra provide essential clues to understanding the universe's expansion. By studying these spectra, scientists can determine the age of galaxies, track the formation of stars, and even pinpoint the birthplaces of planets. Hydrogen's fingerprints are everywhere, embedded deeply in the cosmic narrative, helping us measure the vast stretches of time and space that define the universe. Yet hydrogen's importance extends beyond the boundaries of space. It's a critical element for life as we know it on Earth. Not only is it a vital component of water without which life could not exist, but it also fuels the sun. The fusion of hydrogen atoms into helium within our star provides the energy necessary to sustain life on Earth. Without hydrogen, there would be no sunlight, no warmth, no energy driving the natural cycles that make life possible. Furthermore, the process of stellar fusion, which begins with hydrogen, creates the heavier elements that form the chemical diversity necessary for the development of complex molecules, molecules that are the very foundation of living organisms. Hydrogen's legacy is written across the universe. Its presence ignited stars, fueled galaxies, and created the very building blocks of life. From the birth of the first stars to the formation of planets and the emergence of life, hydrogen has been the silent architect of the cosmos. It is, without question, the essential ingredient in the grand cosmic recipe. The simplicity of hydrogen, coupled with its ability to transform and evolve, has allowed for the stunning complexity of the universe to unfold. Indeed, the formation of hydrogen laid the foundations for the magnificence we observe today in the universe. It powered the stars that lit up the darkness of the cosmos and seeded the universe with the elements required for life. Its presence created the galaxies that spread across space, each one containing millions, even billions of stars, each one a product of hydrogen's transformative power. And as hydrogen continues to fuel the stars, so too does it continue to drive the evolution of the universe, acting as the essential key to understanding not just where we came from, but where we are going. In essence, hydrogen is not merely a gas, it is the very pulse of the universe. From the birth of the first stars to the nurturing of life on Earth, hydrogen has charted the course of the universe's evolution. It is the genesis of everything, the beginning of every light in the sky, and the quiet catalyst for the stars, galaxies, and life itself. Without hydrogen, there would be no universe as we know it. No stars to gaze upon, no planets to inhabit, and no life to sustain. It is the simplest element, yet the most powerful, and its story is written into the very fabric of the cosmos. They begin their journey by fusing hydrogen into helium, the most basic element in the cosmos, igniting the birth of stars. This process, which continues through successive generations of stars, gradually leads to the creation of even heavier elements. When these stars exhaust their fuel, they meet their inevitable fate in a magnificent yet catastrophic event, a supernova explosion. The death throes of these stars are far from meaningless. In fact, they scatter the newly created elements into the surrounding space, enriching the interstellar medium with the building blocks of life and new stars. This cosmic recycling, as it is often called, has played a pivotal role in shaping the rich, chemically diverse universe that we observe today. The scattered elements combine in various ways, contributing to the formation of rocky planets and complex organic molecules, the very foundation of life as we know it. Among these elements, hydrogen stands out. not only because it is the most abundant element in the universe, but also because it serves as a critical tool in our understanding of the cosmos. In the vast expanse of interstellar space, hydrogen behaves in predictable ways, making it an invaluable tool for astronomers. Its presence and behavior help scientists map the universe, tracing the intricate spiral arms of galaxies and unraveling the large-scale structure of cosmic matter. The spectral lines of hydrogen, which correspond to its specific energy levels, serve as cosmic fingerprints, allowing astronomers to measure the redshift of distant galaxies and observe the ongoing expansion of the universe. These spectral signals not only give us a glimpse into the distant past, but also provide essential data for determining the vast distances that separate celestial bodies. Beyond mapping distant galaxies, hydrogen plays a critical role in the formation of solar systems. In nebulae, vast clouds of gas and dust, hydrogen compounds like water are crucial in the development of habitable environments on planets. The presence of hydrogen, both in its pure form and in compounds like water, has been a key ingredient in the creation of planets with the potential for life. Without hydrogen, the evolution of life as we know it would not have been possible. In this way, hydrogen is not just a passive component of the universe, but an active force, contributing to the formation of stars, galaxies, and planets, as well as laying the groundwork for the emergence of life. From fueling the first stars to serving as the essential component for life on Earth, hydrogen's impact on the universe's evolution is profound. Now, let us delve into a concept that challenges our very understanding of the universe: antimatter. This mysterious and elusive counterpart to matter is one of the most intriguing areas of modern physics. Antimatter is not just a theoretical curiosity. It has practical implications that could revolutionize fields from medicine to space exploration. The concept of antimatter was first proposed by physicist Paul Dirac in 1928, emerging from his work on quantum mechanics and the theory of relativity. His groundbreaking equations suggested the possibility of particles with negative energy, a concept that seemed almost absurd at the time. However, this radical idea was validated in 1932 with the discovery of the positron, the antimatter equivalent of the electron, carrying a positive charge instead of a negative one. When matter and antimatter come into contact, they annihilate each other, releasing vast amounts of energy, typically in the form of high-energy photons or gamma rays. This annihilation process is one of the most fascinating phenomena in physics, and one that underpins one of the greatest mysteries of cosmology: the apparent asymmetry between matter and antimatter in the universe. According to current theories, the Big Bang should have created equal amounts of matter and antimatter, yet our universe is overwhelmingly composed of matter. The fact that there is so much more matter than antimatter is a fundamental puzzle that scientists continue to study, hoping to unlock secrets about the origins of the universe itself. Despite the theoretical nature of much of the antimatter research, there are practical applications already in use today. In medicine, positron emission tomography (PET) scans rely on the annihilation of positrons to visualize internal bodily processes, making it a vital tool in medical diagnostics. But the potential of antimatter extends far beyond current technology. The possibility of using antimatter for propulsion in spacecraft, although still speculative and enormously challenging, could one day revolutionize space travel. By harnessing the immense energy released from the annihilation of matter and antimatter, spacecraft could travel across vast cosmic distances, opening up new frontiers for human exploration of the universe. Antimatter, in its essence, is a mirror image of the matter that surrounds us. The most fundamental difference between the two lies in their electric charge. Matter particles like electrons carry a negative charge, while their antimatter counterparts, such as positrons, carry a positive charge. But the differences go deeper than just charge. Antimatter particles have opposite values for other quantum numbers, such as baryon number, lepton number, and strangeness. These properties are conserved in particle interactions and give antimatter a unique and essential role in the universe's laws of physics. While antimatter has yet to be directly observed under the influence of gravity, experiments are underway, including those with anti-hydrogen atoms at the CERN laboratory, in hopes of discovering whether antimatter interacts with gravity in the same way as matter. Perhaps the most dramatic consequence of matter-antimatter interaction is the annihilation that occurs when the two meet. In these explosive encounters, the masses of both particles are converted into energy, typically releasing high-energy gamma rays. This phenomenon is not just a theoretical curiosity, but a potential source of limitless energy. The study of antimatter continues to open up new frontiers in both fundamental physics and practical technology. It embodies some of the most profound mysteries of the universe, while also holding the promise of future discoveries that could change our understanding of space, time, and the very fabric of the cosmos. According to Einstein's famous equation, energy equals mass times the speed of light squared. This relationship forms the basis for some of the most efficient and energetic processes we know in the universe. However, when we look at the interactions of matter particles with themselves, we find something starkly different. These interactions don't result in such complete conversions of mass into energy. It's a fascinating contrast, highlighting how little we truly understand about the underlying mechanics of the cosmos. At the very heart of this mystery lies the existence of antimatter and its elusive properties, which raise profound questions about the universe's evolution. The Big Bang Theory, the prevailing explanation for the origin of the universe, suggests that matter and antimatter were created in equal amounts during the universe's birth. Yet, when we look out into the cosmos, we see that the observable universe is overwhelmingly made up of matter, with antimatter conspicuously absent. Why is this so? The matter-antimatter asymmetry problem, why there is more matter than antimatter in the universe, remains one of the greatest unsolved puzzles in physics. This imbalance doesn't just sit in the abstract, it shapes the very structure and evolution of the universe. The search to explain this discrepancy reveals both the complexity and symmetry inherent in the laws of the universe. Known as baryon asymmetry, this imbalance refers to the striking difference between the amount of matter and antimatter. Despite theoretical models and experimental evidence suggesting that the Big Bang should have produced equal amounts of both, we observe that matter has completely dominated. Why? The standard model of particle physics, which has been the cornerstone of our understanding of particles and forces, tells us that the behavior of a particle and its corresponding antiparticle should be nearly identical. Theoretically, they should annihilate one another when they come into contact, but clearly, this has not happened on the grand scale we observe. Instead, our universe is made up predominantly of matter. So what caused this cosmic imbalance? Theories abound, but one of the most widely discussed involves CP symmetry, a law that suggests the laws of physics should remain unchanged if a particle is replaced by its antiparticle, charge conjugation, C, and if its spatial coordinates are reversed, parity inversion, P. Yet, experiments have observed violations of CP symmetry in certain interactions governed by the weak force. These observations suggest that under specific conditions, the universe might exhibit a preference for matter over antimatter. This revelation has huge implications, especially when considering the nascent state of the universe. One of the most compelling frameworks proposed to explain this phenomenon is baryogenesis, which suggests that the early universe underwent a phase that produced more baryons, particles like protons and neutrons, than antibaryons. This would have resulted in the residual matter that makes up the stars, planets, and galaxies we see today. Baryogenesis is thought to involve new physics beyond the standard model, including processes that violate CP symmetry and favor the creation of matter. Within the ultra-hot, dense environment of the early universe, processes like sphalerons could have played a role in converting baryons and leptons and their corresponding antiparticles into each other, violating conservation laws and leading to the asymmetry. Efforts to solve this great mystery are ongoing, with particle accelerators like the Large Hadron Collider at CERN offering a venue for testing these theories. Observations of the cosmic microwave background and distant galaxies also provide critical data that may eventually offer insights into the primordial forces that shaped the universe. Unraveling the matter-antimatter asymmetry would not only explain why matter outnumbers antimatter in the observable universe, but also unlock a deeper understanding of the conditions and laws that govern the birth of the cosmos. The matter-antimatter asymmetry is a crucial element in the formation of protons, a pivotal chapter in the grand narrative of the universe. In its earliest moments, the universe was a hot, turbulent sea of energy, giving rise to pairs of particles and antiparticles. According to prevailing theories, these pairs should have annihilated each other completely, leaving behind a universe without matter. Yet, the universe we observe today is overwhelmingly matter-dominated, indicating that something in the early moments of cosmic history tipped the balance. This imbalance, scientists believe, influenced the formation of protons, the building blocks of atoms, and, by extension, all matter. For reasons that are not yet fully understood, there was a slight excess of matter particles, specifically quarks, over their antimatter counterparts. As the universe cooled, these quarks clumped together to form protons and neutrons. This surplus of matter allowed protons to survive, bond with electrons, and form the atoms that gave rise to stars, planets, and, eventually, life. Thus, the matter-antimatter asymmetry is not just a footnote in cosmic history. It's a cornerstone of our material existence. It affected the very formation of protons and, in turn, shaped the cosmos itself. Several theories have been put forward to explain this imbalance, with one of the most prominent being CP violation. This concept suggests that the laws of physics do not apply equally to particles and their antiparticles, allowing for processes that favor the production of matter over antimatter. While CP violation has been partially observed in experiments with particles like kaons and B mesons, the full extent of its role in the early universe remains a tantalizing mystery. As our understanding of the universe deepens, the search for an answer to the matter-antimatter asymmetry continues, offering the potential to reveal new physics beyond our current grasp. In the grand scheme, solving this puzzle could illuminate not only the origins of the universe, but also the fundamental nature of reality itself. Another intriguing concept is leptogenesis, a theory suggesting that the decay of heavy neutrinos in the early universe could have created an imbalance between leptons, such as electrons and antileptons. This excess of leptons, if it occurred, could then have been converted into the baryon asymmetry, the imbalance between matter and antimatter, which we observe today. According to this theory, processes governed by the electroweak force, one of the four fundamental forces of nature, would have facilitated this conversion. Leptogenesis presents an exciting avenue for understanding why the observable universe is almost entirely composed of matter, with very little antimatter. The underlying processes that might have caused this imbalance remain unclear, but they're a central focus in particle physics and cosmology. Beyond leptogenesis, another theory proposes the existence of new physics beyond the standard model of particle physics. This theory suggests the presence of additional, yet-to-be-discovered particles or forces that could have contributed to the imbalance between matter and antimatter. These hypothetical particles could have influenced processes in the early universe, favoring the production of matter over antimatter. Each of these theories seeks to tackle one of the most perplexing mysteries in modern physics, the matter-antimatter asymmetry, while also helping us understand the very origins of the universe itself. Despite the allure of these ideas, none of them have been definitively proven. However, ongoing experiments from particle accelerators to cosmological studies continue to search for evidence that could either confirm or refute these groundbreaking theories. As scientists continue to push the boundaries of what we know, they also inch closer to unraveling the origins of the universe and the fundamental forces that govern it. The quest to understand this asymmetry not only challenges our comprehension of the fundamental particles and forces of nature, but also brings us one step closer to unlocking the secrets of the cosmos. In parallel to these fundamental questions about matter and antimatter, another cosmic puzzle captivates scientists: dark matter. Despite being invisible and undetectable by traditional telescopes, dark matter plays a crucial role in the structure and evolution of the universe. In fact, it makes up about 25% of the universe's total mass energy density, vastly overshadowing the visible matter we are familiar with, such as stars, planets, and living organisms, which only account for about 5%. The term dark refers to the fact that this mysterious substance neither emits, absorbs, nor reflects any form of electromagnetic radiation, rendering it entirely invisible to traditional forms of detection. Our understanding of dark matter began in the 1930s with Swiss astronomer Fritz Zwicky, who first inferred its existence through his observations of the Coma cluster. Zwicky noticed that galaxies within this cluster were moving much faster than expected, based on the cluster's visible mass. This suggested the presence of an unseen mass contributing additional gravitational pull, which we now attribute to dark matter. Further confirmation came decades later in the 1970s when astronomers Vera Rubin and Kent Ford studied the rotation curves of galaxies. They found that stars and galaxies were rotating so quickly that they would fly apart if only visible matter were present. This implied the presence of additional unseen mass, which was later identified as dark matter. More evidence came from the phenomenon known as gravitational lensing, where light from distant objects is bent by massive objects like galaxies and galaxy clusters. The amount of lensing observed was far too great to be caused by visible matter alone, providing further proof of dark matter's existence. Despite this compelling evidence of its presence, the exact nature of dark matter remains one of the greatest mysteries in modern physics. We have a solid understanding of its role in the universe, helping to form and stabilize galaxies, but its composition is still unknown. Several candidates for dark matter particles have been proposed over the years, such as weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. Yet, despite numerous experiments and theoretical studies, none of these particles have been conclusively detected. Understanding dark matter is not just crucial for cosmology, but for bridging the gap between the physics we know and the unknown realms of the universe. By unlocking the secrets of dark matter, scientists hope to gain insight into the fundamental forces that shape our universe, pushing the boundaries of our understanding of both the known and the unknown cosmos. Dark matter serves as one of the most mysterious and fundamental forces in the universe, playing a pivotal role in shaping the cosmos we observe today. Invisible to our eyes, yet undeniable in its influence, it acts as the unseen scaffolding, subtly guiding the formation and evolution of the universe's grand structures. Its impact began in the earliest moments of the cosmos and continues to reverberate through time, influencing everything from the smallest galaxies to the largest superclusters. In the chaotic aftermath of the Big Bang, the universe was initially a nearly uniform soup of particles, a hot and dense expanse where all matter was intertwined. However, even in this turbulent state, tiny fluctuations in density existed, slight variations that would prove to be crucial. While ordinary matter, known as baryons, was subject to electromagnetic forces and radiation, dark matter remained unaffected by such forces, allowing it to remain cold and stable. This crucial difference allowed dark matter to begin clumping together under the force of gravity, forming dense regions in an otherwise uniform universe. These clumps of dark matter served as the cosmic bedrock upon which the visible universe was built. Gravity, the only force that dark matter interacts with, created gravitational wells, regions of stronger gravitational pull. These wells drew in ordinary matter, beginning a process that would eventually give birth to the first stars and galaxies. Without dark matter's gravitational influence, this process would have been far less efficient. The pressure and temperature of the primordial gas would have been too great for galaxies and stars to form as they did. In essence, dark matter's invisible touch laid the groundwork for the universe's first luminous structures. As the universe continued to evolve, dark matter's influence extended beyond individual galaxies to the vast and complex cosmic web. Galaxies did not form in isolation. Instead, they gathered in groups and clusters bound together by gravity. These clusters of galaxies, along with clouds of gas and dark matter, formed the universe's largest structures. These clusters were connected by long, dark strands of dark matter, weaving a vast, interconnected cosmic web. The distribution of dark matter played a crucial role in the formation and arrangement of this web, affecting the size, shape, and positioning of galaxy clusters. Through sophisticated cosmological simulations, scientists have been able to model how dark matter shapes the universe's structure. These simulations, which take into account the gravitational effects of dark matter, show that galaxies and galaxy clusters form in a way that mirrors our observations. The results are strikingly accurate, depicting a universe shaped by the gravitational pull of dark matter. From the smallest galaxies to the largest superclusters, dark matter's presence enhances the clumping of matter, creating the intricate cosmic structures that we see today. As a result, dark matter functions as the invisible backbone of the universe, around which visible matter organizes itself. Its gravitational influence is essential for the formation of galaxies, stars, and larger cosmic structures. It has played a crucial role in the transition of the universe from its smooth, homogeneous beginnings to the vast, complex, and filamentous structure we observe now, a structure that spans billions of light years. However, the connection between dark matter and proton formation is not a direct one. Proton formation, a critical process in the early universe, occurred during an era known as Big Bang Nucleosynthesis, BBN, a few minutes after the Big Bang. During this brief window, as the universe cooled, quarks combined to form protons and neutrons, which then fused into the first nuclei, primarily hydrogen and helium. Dark matter, on the other hand, was not involved in this process, but played a more crucial role in the universe's structural evolution long after the initial formation of protons and nuclei. It acted as the cosmic framework, guiding the clustering of baryonic matter into stars and galaxies, laying the foundation for the universe's complex architecture. Without dark matter, the universe we know would be a very different place, without the dense structures, galaxies, or clusters that we observe. Its invisible yet essential presence continues to shape the very fabric of the cosmos, helping to form everything from the smallest star systems to the largest galaxy superclusters. In understanding dark matter, we unlock the secrets of the universe's creation, its evolution, and perhaps its ultimate fate. Although dark matter does not interact with regular matter, or baryonic matter as it is scientifically known, through the electromagnetic force, its gravitational pull is essential to the development of the universe. In the early moments after the Big Bang, the universe was incredibly uniform. However, tiny fluctuations in density began to emerge, and these fluctuations were amplified by the gravitational influence of dark matter. Over time, these density variations evolved into the large-scale structures we see today, from galaxies to galaxy clusters. While dark matter's role wasn't directly involved in the creation of protons, it was undeniably entwined with the fate of these particles and the broader process of cosmic evolution. Once protons were formed, the gravitational pull exerted by dark matter began to gather them together with electrons and neutrons. This pull was a crucial force that eventually led to the formation of atoms, stars, and galaxies. It is in this complex interaction between dark matter and baryonic matter that the very architecture of the cosmos was shaped. Without dark matter's gravitational influence, the universe as we know it, with its galaxies, stars, and planets, might never have formed in the way it did. The relationship between dark matter and the formation of protons, and, by extension, atoms, can be understood as one of context rather than direct interaction. Dark matter didn't directly create these fundamental building blocks of the universe, but its gravitational influence was the driving force behind their aggregation, which allowed for the observable structures of the cosmos to take shape. The distribution and evolution of galaxies across the universe owe much of their existence to this unseen but powerful force. Fast forward to today, and modern particle accelerators, like the Large Hadron Collider, LHC, at CERN, are taking us back in time to simulate the conditions of the early universe. These accelerators recreate the extreme energy densities that existed just after the Big Bang, allowing scientists to probe the forces that shaped our universe's earliest moments. By accelerating particles to nearly the speed of light and colliding them, LHC generates temperatures and energies that mirror those of the first fraction of a second after the Big Bang. This process not only mimics the physical conditions of that time, but also recreates the high-energy state where the fundamental forces of nature, electromagnetic, weak, strong, and gravitational, were once unified. The debris produced in these collisions offers a wealth of information about the particles and forces that governed the early universe. These are conditions that are impossible to observe under the cooler, less dense environment of today's universe. One of the primary objectives of simulating the early universe in particle accelerators is to recreate and detect quarks and gluons. These particles are the fundamental components of protons and neutrons. In the universe's infancy, it was so hot and dense that quarks and gluons existed freely in a state known as quark-gluon plasma. This plasma eventually cooled and condensed to form protons, neutrons, and later the atoms that constitute matter as we know it. Modern accelerators have already succeeded in recreating brief instances of quark-gluon plasma, offering unprecedented insight into the behavior of matter under extreme conditions. But the potential applications of these experiments extend beyond the formation of ordinary matter. Particle accelerators also offer a unique opportunity to explore dark matter. Though dark matter does not interact with light, making it invisible to telescopes, it might be possible for particle accelerators to produce new particles that could be dark matter candidates or reveal clues about its nature. By studying the results of particle collisions and the conditions they replicate, scientists hope to unlock the secrets of dark matter. This could lead to answers about its elusive properties and how it fits into the grand puzzle of cosmic evolution. In essence, particle accelerators act as time machines, giving scientists the ability to peer back into the distant past to moments mere fractions of a second after the universe's creation. These experiments provide a closer look at the high-energy, high-density conditions that prevailed at the dawn of time. With each discovery, we inch closer to understanding the universe's most profound mysteries, from the nature of dark matter to the forces that shape the earliest moments of cosmic evolution. While we now know that protons are abundant throughout the universe, a laboratory setting is one of the few places where they can be directly created through particle collisions in modern accelerators. Although protons themselves are stable and fundamental to the atomic nucleus, along with neutrons, creating them in a controlled laboratory environment requires sophisticated, high-energy experiments. In this way, particle accelerators do more than just simulate the past. They also allow us to recreate the very building blocks of the universe, helping to unveil the forces that govern our existence. The quest to unravel the mysteries of proton formation is an extraordinary journey that captivates the curiosity of scientists from all corners of the world. This journey is a delicate dance, where diverse fields of research intertwine, presenting both a rich tapestry of challenges and endless questions. At the heart of this scientific odyssey lies one of the most elusive puzzles, understanding the proton's internal structure, as well as the forces that bind its fundamental constituents, quarks and gluons, together. Despite their incredibly small size, protons contain a world of complexity, governed by the mighty strong force, one of the four fundamental forces of nature. This force holds the quarks together, but how does it operate at such minuscule scales? To begin understanding this puzzle, scientists turn to quantum chromodynamics, QCD, a theory that offers a framework for describing these interactions. QCD explains how quarks interact with each other via the exchange of gluons. The theory is robust and has been successful in many respects. Yet, it is notoriously difficult to solve when applied to low-energy scales, such as those involved in proton formation. This difficulty has made it one of the most challenging aspects of modern physics. At the heart of proton formation lies the structure of the proton itself. Protons are composed of three smaller particles, two up quarks and one down quark. These quarks are bound together by the strong force, which is mediated by gluons. The force that holds them together is immensely powerful, but the mechanisms by which it operates are still not fully understood. One of the most significant challenges in studying protons is determining the charge radius, which is a measure of the proton's size. Recent experiments aimed at measuring this radius have led to conflicting results, sparking intense debates among physicists. This disagreement emphasizes the need for more refined experimental techniques and advanced theoretical models. Another critical area of research centers around proton decay, a process predicted by various grand unified theories, but which has never been observed experimentally. If protons were to decay, it would mean that they are not truly stable particles. Instead, they would have an incredibly long lifetime, suggesting that even the most fundamental building blocks of matter might one day decay into nothingness. Such a discovery would have profound implications for our understanding of the stability of matter itself, potentially altering our conception of the universe's ultimate fate. Each of these challenges represents a piece of a larger, intricate puzzle, one that drives relentless scientific inquiry and technological innovation. The standard model of particle physics provides a foundational framework for understanding the universe's fundamental particles and forces, including the formation of protons. Within the standard model, quarks play a central role. Quarks, the fundamental building blocks of protons, interact via the exchange of gluons, which mediate the strong force that holds them together. This interaction is described by quantum chromodynamics, which explains how quarks carry a type of charge called color charge. This term, however, is not related to visible colors, but instead derives from a mathematical analogy to primary colors and their mixing properties. The strong force, as described by QCD, is unique in that it gets stronger as quarks move farther apart and weaker as they get closer together. This counterintuitive behavior is what allows quarks to remain confined within protons. The energy involved in this confinement is so strong that it prevents quarks from escaping, creating a stable particle. However, the complexity of these interactions means that scientists must rely on sophisticated mathematical models and powerful computers to simulate the behavior of quarks and gluons within a proton. Despite the vast success of the standard model in explaining proton properties such as charge and composition, it is far from complete, particularly when it comes to understanding the proton's mass and size. These properties emerge from the intricate dynamics between quarks and gluons, and unraveling this process is a major goal of current research. Yet, the search for a deeper understanding of proton formation doesn't stop at the standard model. Many scientists are exploring alternatives and extensions to this well-established framework. One such theory is supersymmetry, often abbreviated S-SLI, a theoretical construct that proposes a partner particle for each particle in the standard model. The goal of supersymmetry is to address several unresolved issues in the standard model, such as the hierarchy problem, which relates to the vast disparity between the strengths of different fundamental forces. Supersymmetry also offers the potential for the unification of forces at high energy scales. If supersymmetry were true, it could have profound implications for our understanding of proton formation, potentially introducing new particles that could alter or enhance the processes that govern proton stability. This could open up entirely new pathways for understanding the nature of matter and the universe itself. As we continue to push the boundaries of knowledge, the formation of protons remains a central puzzle that has yet to be fully solved. Yet, this ongoing exploration, driven by both theoretical insight and cutting-edge technology, holds the promise of revealing new layers of the universe's deepest secrets. The journey is far from over, and with each new discovery, we come closer to understanding the very essence of matter and the forces that shape our reality. Another intriguing avenue of research is the exploration of hypothetical particles, often referred to as prons. These particles are theorized to be subcomponents of quarks and leptons. If such particles exist, they could reveal a deeper layer of structure within protons, challenging the current belief that quarks are fundamental building blocks of matter. This potential discovery would radically transform our understanding of the fundamental nature of matter, offering new perspectives at the most minuscule levels of the universe. It would open the door to a new chapter in particle physics, where the very foundation of our reality may be far more intricate than we have ever imagined. In parallel, theories of quantum gravity, such as loop quantum gravity, LQG, are at the forefront of attempts to reconcile the seemingly incompatible worlds of quantum mechanics and general relativity. LQG proposes a quantum description of space-time itself, which could help us understand the fundamental nature of gravity and the universe's structure at the quantum level. Though LQG primarily focuses on the fabric of space-time and gravitational phenomena, it offers a tantalizing possibility that quantum gravity could also illuminate the forces governing proton formation. However, while the implications of these theories are profound, it's crucial to remember that they remain speculative at this stage. awaiting experimental verification to confirm their validity. Even though these ideas are still largely theoretical, the search for phenomena that challenge the standard model of particle physics is pushing the boundaries of science. Proton decay, for instance, remains a major mystery that scientists are eager to solve, as does the investigation of unusual proton behavior that might point to deeper, undiscovered principles. These anomalies could eventually lead to groundbreaking discoveries, offering a more unified and comprehensive theory of the universe. This new framework could blend the standard model with fresh insights, providing solutions to the long-standing mysteries of proton formation and the nature of matter. At the heart of understanding proton formation is quantum chromodynamics, QCD, a cornerstone in the study of the strong nuclear force, one of the four fundamental forces of nature. QCD is responsible for binding quarks together to form protons and other hadrons. Unlike electromagnetism, where like charges repel and opposite charges attract, QCD introduces a unique concept known as color charge. Despite the name, color charge has nothing to do with visual colors. Rather, it is a way of describing the interactions between quarks and gluons, the particles that mediate the strong force. In QCD, quarks can carry one of three color charges, and gluons carry color force, making them fundamentally different from the force carriers of other forces. One of the most fascinating properties of QCD is that the strong force actually becomes stronger as quarks move apart, a phenomenon known as confinement. This ensures that quarks are never found in isolation, but are always bound together within hadrons, such as protons. When quarks try to separate, the energy of the strong force between them increases to the point where it becomes energetically favorable for a new quark-antiquark pair to spontaneously form from the vacuum, thus keeping the quarks bound inside protons and other hadrons. This intricate behavior prevents quarks from ever existing alone under normal conditions, cementing the stability of matter at the most fundamental level. In contrast to confinement, QCD also explains a phenomenon known as asymptotic freedom. This means that quarks behave almost as free particles when they are extremely close to each other, allowing for some degree of movement within the proton. This dual behavior of quarks, constrained at larger distances but freer at closer ranges, provides the stability necessary for the proton's existence. The major challenge with QCD lies in its complex mathematics. The equations governing this theory are so intricate that solving them exactly is currently beyond our capabilities, particularly in the case of physical situations involving multiple quarks. To make progress, researchers rely on powerful supercomputers to perform numerical simulations through a technique called lattice QCD. These simulations allow scientists to study proton formation and investigate the properties of the strong force in a way that is not feasible with traditional analytical methods. Through these advanced computational efforts, QCD has made significant strides in enhancing our understanding of the internal structure of the proton. It has opened windows into the deep, hidden layers of matter, offering invaluable insights into the forces that shape the very fabric of the universe. These ongoing efforts, though still in their early stages, are gradually piecing together the complex puzzle of proton formation and helping us uncover the mysteries that have fascinated physicists for generations. As we continue to explore the depths of these theories, we may soon unlock the answers that have eluded us for so long, forever altering our perception of the universe at its most fundamental level. Future experiments probing the mysteries of proton formation promise to push the limits of our understanding and technology, opening new avenues of discovery in the world of particle physics. These groundbreaking endeavors are designed to examine the very essence of matter, testing the intricate predictions of quantum chromodynamics, QCD, and exploring territories beyond the established standard model of particle physics. One of the key experiments in this pursuit is the Electron-Ion Collider, EIC, a state-of-the-art facility set to be built at Brookhaven National Laboratory in the United States. The EIC is set to accelerate electrons and protons, or heavier ions, to near light speeds, allowing them to collide in a controlled environment. This will give scientists the unprecedented opportunity to study quarks and gluons, the very building blocks of protons, with incredible precision. By understanding how these fundamental particles interact, Scientists will be able to better understand the proton's intrinsic properties, such as its mass and spin. This experiment is poised to reveal essential details about how the simplest yet most fundamental building block of matter, the proton, behaves at the quantum level. Another monumental experiment in this field is the planned upgrade of the Large Hadron Collider LHC at CERN, known as the High Luminosity LHC, HL-LHC. The goal of the upgrade is to significantly increase the number of particle collisions, thus enabling scientists to collect vastly larger datasets. With this expanded dataset, physicists aim to detect rare processes and particles that could potentially point to phenomena beyond the standard model. These discoveries could shed light on the fundamental forces that govern proton formation, potentially opening new doors to understanding the stability of protons themselves. The HL-LHC could not only enhance our knowledge of protons, but also revolutionize our understanding of the universe's underlying laws. In addition to these experiments, advancements in lattice quantum chromodynamics, lattice QCD computations offer another crucial piece to the puzzle of proton formation. With the help of supercomputers, researchers can simulate the conditions and interactions that lead to proton formation, examining these processes at an unprecedented scale of space-time points. These theoretical simulations are indispensable for testing QCD predictions, especially in regimes that are difficult or impossible to explore experimentally. By combining cutting-edge computational techniques with high-energy particle collisions, these experiments will paint a comprehensive picture of the proton and its formation. Together, these efforts represent a multifaceted approach to understanding the proton. Through the combination of high-energy particle collisions, precision measurements, and advanced theoretical simulations, scientists are well equipped to uncover the secrets of proton formation. These revelations could potentially pave the way for new physics that transcends our current models, opening up entirely new frontiers of discovery. The implications of understanding proton formation are profound. The proton is the cornerstone of matter itself, forming the building blocks of atoms and, by extension, all of the chemical and biological processes that define our universe. Unraveling the mysteries of proton formation could have far-reaching consequences, spanning from particle physics to cosmology. One of the most intriguing possibilities is gaining deeper insight into the strong force, the fundamental force that binds quarks together within protons. Such an understanding could reveal new aspects of quantum chromodynamics, the theory that governs these interactions, and could offer critical clues about the formation of matter in the early universe shortly after the Big Bang. Understanding proton formation could also provide valuable insights into the fate of the universe. The concept of proton decay, a process predicted by several grand unified theories but never yet observed, could have profound consequences for our understanding of the universe's ultimate destiny. If protons were found to decay, even over exceedingly long timescales, it would indicate that matter, as we know it, is not eternally stable. This discovery would confirm some of the most ambitious theories in physics, while offering an entirely new perspective on the life cycle of the cosmos. In addition to these theoretical breakthroughs, a better understanding of proton formation could drive major technological advancements. A more profound comprehension of the strong force could lead to breakthroughs in nuclear fusion research, offering the potential to develop clean, sustainable energy. It could also have significant applications in the realm of quantum science, potentially unlocking new quantum technologies that are currently beyond our reach. Perhaps most exciting of all, advancements in proton formation research could illuminate the dark matter puzzle. Dark matter, which accounts for a large portion of the universe's mass, remains undetectable through conventional means. However, new discoveries regarding proton formation could uncover previously unknown particles or forces that might explain the elusive nature of dark matter. These findings could offer profound insights into the structure of the universe and the fundamental forces that govern it. In short, understanding proton formation isn't just about unlocking the mysteries of a single particle. It's about unraveling the very fabric of reality itself, from the quantum world to the vast expanses of the cosmos. The discoveries made in the field of proton formation have the potential to reshape our understanding of the universe, offering new insights into the creation of galaxies, stars, and planets. So, what are your thoughts on the origins of everything? Did it all start from nothing, or could it have been created by something far beyond our current comprehension? Leave your thoughts in the comments below, and don't forget to subscribe to our channel, Starflux, for more captivating documentaries like this one. Thanks for watching.